If they're so happy to calculate their own capital industry or purchase reagents and consumables for running metabolomics assays, the method, as I already said, are highly standardized and has been fully validated, so users don't need to do any method development for their metabolomics project.
We want to make sure that every step in the process is as easy as possible and as efficient as possible. So that's why we developed our kit running robot to prepare samples and then run through the steps. The robot itself is as easy to use as possible. You just have to set up, load in samples, load in place for set to Presto, it'll do what it does.
I think one of the areas that we try to work on development of these kits is to provide a diverse array of compounds. We have a particular focus on organic acids, which are vital, important in driving diseases and disease biomarkers. And they're critical in immune metabolism. Then they're going to play a role in presenting gut microbiome. And additionally, we've also tried to include a range of other metabolites or compounds that are useful as biomarkers.
We created a custom pipetting robot. It can deliver as low as 10 microliters, as high as 100 microliters to any area, any region of a cancer system at a time. It can use that to add components into our well plates and to mix ingredients and to make sure that they're manufactured.
There's testing the 138 here. They got a specialized offer for the outgoing users and see if it's but there was an app on there to trust that every step from that and create a problem. Make sure it's consistent off every time.
This is working molecular insight into what we're looking for. And it's because metabolomics gives us this molecular dimension, this molecular phenotype. We say it's really useful for applications in precision, personalized medicine, precision, personalized nutrition. And what we're able to do with the quantitative applications, especially these kits, is to identify several readouts, comprehensive readouts, versus molecular phenotype. You're not just measuring your weight, you're measuring 1,400 parameters at the same time. And the list keeps on growing. We're astonished at how people are using these kits. And again, just pulling back to the fact that these are reproducible, quantitative, they're inexpensive, and they're fast.
Hi, my name is Translational, and I'm quality manager for the Central Visual Lab. We are a ISO lab, and we have ISO 17225 and 151 in hand. People believe that the quality is handled and it is not only investment of time and resource to implement quality in research labs. However, it is important to recognize that implementing quality in the research lab comes with significant benefits.
And one of the major benefits is getting consistent results. Reproducibility crisis has been a big issue in research lab, and it has hindered the scientific progress and innovation. So by having a strong quality management system in research lab that can lead to improved lab efficiency in the use of resources, reduced rework, and longer long-term operational cost. Quality management is basically having two elements. One is the quality assurance and the quality control. Quality assurance focuses on the process of policies and gives us a confidence in our results. In our lab, we practice quality assurance by implementing competency and training program to make sure that everyone working in our lab have a good training done and they are skilled enough to do the work they are assigned. In addition to that, we also make sure that our instruments are calibrated, they are well maintained, and we have SOPs and validation program. So as process certification actually serves as a quality mark that assures our client that we believe in quality and we are committed to demonstrate quality product. By practicing ISO standards in our lab, it actually benefits in continuous improvement because we can monitor our non-conformances and we can implement corrective actions. In addition, we are also audited by the third-party auditors, so that gives us a confidence in the quality we have in place as well as it helps us to improve our quality.
The reason I wanted to take this course is because I'm interested in clinical chemistry as a career path, and I was excited to get more hands-on lab work with the whole crew of analytical chemists here.
Specifically my PhD project, we are working with metabolomics applied to animal science, and this is my first experience using metabolomics analysis, so I hope that this course can help me to have a good base for learning about lab analysis and data analysis, so then I can use in my project.
I'm pretty excited. It's just a day one, so still we have like four more days to go. So yeah, I am pretty excited.
What I like most about this course is, aside from the thorough technical lessons that we are learning with instrumentation and data processing, we're introduced to a lot of very useful resources and databases that we can use for our everyday work.
I think so far about the course I've liked the hands-on approach. I think everyone here has answered so many of my questions that I've had for years about metabolomics and about the methods that they use.
And I found Tammy and Alan very helpful. They gave me a couple of tips to optimize this method.
I enjoyed every aspect of it. Even though it seemed like a 5-day long hands-on course that goes from 8 to 5, time just went by really fast.
I want to say thank you to Dr. Richard and Timmy for this opportunity. This has really helped me a lot.
Hi everyone, morning. It's a big pleasure for me to be with you here in the closing of the workshop Making Metabolomics Matter, Translational Precision Medicine Applications. For me, it's an honor just to introduce Dr. Cristina Andres La Cueva, who is with us today. Cristina Andres La Cueva is a professor of nutrition, food science, and gastronomy, Faculty of Pharmacy and Food Science in University of Barcelona, and ICRIA Academia researcher. She is coordinator of the Consolidated Research Group, Biomarkers and Nutritional and Food Metabolomics, group leader in the Biomedical Research Network on Frailty and Healthy Aging, member of the Food Innovation Network of Catalonia. Her research focuses on the characterization of healthy eating patterns through studies of adherence and medical and metabolomic profiles or metabotypes, associated with diet, disease risk prevention, and healthy aging through a metabolomic approach. She carried out her postdoctoral stay at Human Nutrition Research Center on Aging in University of Boston, USA, and subsequent research stays in France, UK, and Edmonton, Canada. She is a project coordinator of the European Institute of Innovation and Technology and various international joint programming action. She has published more than 250 scientific articles in international journals. Christina, the floor is yours.
Here you are. And something is missing. I'm enthusiastic research. So as all of you, because to be here, to spend 1 week learning and ready for new knowledge, so I'm sure that all of you are also a great enthusiastic. So with this introduction, yes, now I can start. So this is well, we will divide I will put the timing. Do not abuse of your time. Estoy encantada de estar aquí. Sí. Change to the English. So this is metabolomic-based dietary and microbiota biomarkers in nutritional epidemiology, challenge and opportunities for healthy aging research. So this is, I will use this time to present all of my team for the first time. It's super important because the research, metabolomics matters, but people more. So, and as the teamic team, so as my lab team. So here we have a multidisciplinary team where there are chemistry, biologists, bioinformaticians. So, and all of us, we can deal the research that we will present to all of you. And for sure, as we came from a public institution, the University of Barcelona is a public institution, we also have to provide and to try to transmit our research to our society. And this was one photo that we were trying to explain how microbiota works for children and for society, and we did our best. So our research is based on these 3 pillars. So for dietary patterns, polyphenols, we have one research focus in dietary assessment. Another, so what happened when we eat all of this? So analyzing the human metabolome and also all the biomarkers that we will explain, and also obviously the effect that have in the health. Our research lines are all of this. I will share with you my presentation, but we have research in nutritional biomarkers, also development of food composition tables, development of databases, standardization of metabolomic analysis, bioinformatics tools for biological interpretation, some precision nutrition studies, dietary patterns, and also the last one is to try to pack all of this and provide recommendations for society. So scientific evaluation of food, nutrition and health, and in society. So I'm developing of guidelines. This is our dream. Not always we get this, however. As academic, we work on four pillars. So the academia, the research. Also, we have to provide the return for try to valorize our research and to be in contact with industry. And for sure, what we call RI is science with and for society. And with these 4 pillars, we try to get funds to make things happen really. So our funders are in these four pillars. So some examples of all of these. Next steps, I will divide my presentation in these 4 big points. So I will start with the exposome era, not just Taylor Swift era is the exposome era. So precision nutrition and experience from the GPI Healthy Diet for Healthy Life. It was an European initiative, and we participate in several of these actions. Next, I will be focused in some methodology aspects, so on developments, multi-target, quantitative, plan for exposome-based multi-metabolomics. And the last one is some challenge and opportunities for healthy aging. So in this exposome era that we can call, so I will start with, this was a photo in one of the Spanish newsletters. It was shocking, and just to serve to say, oh, we are invaded of plastics. So, wow, we didn't know that. So, and this, when we see this shock, this is a bird with a plastic, okay, blah, 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 blah. However, how can science, real study this is by means of analyzing samples. So I don't know if you can, no, you cannot read, but there is said, so all of this, the analysis of urine samples demonstrate us that the plastics are arriving to the body. So this is why biomarkers is so important, further than this notice. So this is residuos plásticos hasta en la orina. Obviously this, it's important. And this is not a little or small aspect, because it's not easy to analyze this. For this, the improvements in methodology will allow us to increase the profile and for what we are real exposure, so what entering our body, we can say. So obviously on the left side is the more fancy message, no? We live in a soup, plenty of substance that make us fat and get ill. Okay, but this substance we need to translate in biomarkers, and biomarkers that we can quantify, and in this would let us the opportunity to in an epidemiological studies to provide high quality science. So for that is our pillars are focused in these three aspects. So this exposome era that we can say, there are human exposome encompass exposures to environmental factors through a través de toda la vida, starting from conception and pregnancy until during the whole lives. So these environmental factors, for sure, are diverse and interact each with others. So this is important. So because we have some contributors factors in the around that as behavior, financial status, social capital, urban. So all of this is interacting with our exposure. So the exposures in the next steps are concrete, depends on the physical activity, life factors, diet, pharmaceutics, microbiota for sure, chemical pollutants, air pollutants, and all of these confirm we are exposed to all of this, and we will interact with our body, and we expect to follow them as by means of these biomarkers. So this is not I'm enthusiastic, but I'm not alone. So this is obviously there are a huge amount of scientists that are aware of this, and even in our case, from also the European community that is potentiated the study of this exposome. So this is how has increased this exposome literature since in the last years. So, and there is some. This is the small. It's quite new, as it started for the first time in 25. It was described for the first time as all exposures from consumption onwards, including those from lifestyle, diet, and environment. further, it was for some time functionalized. So that means that it was to speak about consider the cumulative measures of this environmental influence and associated with biological response through the lifespan. So including exposures from environmental, diet, behavior, and also the endogenous process. So, and obviously, it has it's important in our in the health on the public health that we will see later. This is so as far as the technology is improving, and we are now more able to quantify or to these microplastics and nanoplastics that these are not for sure easy. So this was one in New England that came in Mars that for one of the first time to see in a high quality science the relation of the microplastics with, in this case, atheroma or cardiovascular events. So we will see more science on this relate. So there are some facts and figures in Europe. 20% of the deaths in Europe are related to environmental factors. Also, 400,000 premature deaths every year in the European community are due to the air pollution. So this is the environment. So obviously, it's a significant determinant of the two top causes of death in Europe is heart disease and stroke. Another data. This is we know the endocrine disrupting chemicals. So we know that we are exposed through inhalation to food and water consumption, so also from mother to fetus, and we know more than 1,500 chemical compounds. But all of these chemical compounds obviously has a repercussion in the. It's great to. When you cannot speak in English to your audience, understanding Spanish, I'm really grateful to all of you. So it costs a lot in economical terms, and however, we need validation in big cohorts, and in another, lately, some of them, there has been already validating in independent cohorts. So in this first part, we can see that this metabolome and the exposome are closely related concepts. Exposure is a complex phenomenon, and the exposome strives to assess the complexity of different exposures that we are open to. So, and the compound identification remains a key bottleneck. So this is. So next step in the agenda, so we'll speak about the precision nutrition and some examples. I will try to be more quick. So obviously at the end we have some questions, which is what is the effect of the diet, which compound of the diet is healthier, mechanism of action, recommended quantity, is the same for all? For sure it's not the same for all. So, and there are this, of course, this interindividual variability that we know, the phenotypic difference between individuals. We will explain later for this. So, the effect of dietary change, obviously, and the individual's response also of the diet. We know responders and non-responders to some diet, some drugs, so we know this fact. So this is, so its aim, the precision nutrition, is, as we say, it's aimed to develop an individualized or feasible dietary intervention based on the nutrition phenotype of an individual created from the integration of genetics, metabolic profile, environmental factors, and this with the objective of preventing and treating chronic disease. See, also considering population subgroups. On this related, I will present one of our works that we published recently based on dietary fiber intake and cognitive decline risk in community living older adults. In this case, so the hypothesis was higher dietary fiber would have a protective effect on cognitive decline in older adults. Like this, big, thinking big. Objective, so evaluate the relationship between dietary intake and incidence cognitive decline in the Chianti study. This is in Chianti study, it's a follow-up of 15 years that we have data from all of this. I will not go deeply. So, and we analyze, in this case, we analyze the dietary assessment. So in this case, the consumption of fiber in grams a day. So, and we stratify, so we saw that fiber consumption was not significantly associated with lower risk of cognitive impairment during these 15 years of follow-up in the general population. However, when we stratify analysis by ApoE haplotypes, show that higher fiber intake was a significant protective effect of the development of cognitive impairment, only in participants with a specific haplotype. So these conclusions are, I already read that. So that this higher intake of fiber, dietary fiber, did not affect in the same to all of them, just to one group. This is. In this experience, so the next step, I would like to share with you some results, what we call this European initiative that led us also the opportunity to meet Dr. Wisher and all that team, because he was also participating in some of them. So we call one was football, maple, Deco Plus, Digumet. We will go one by one, just showing with you some results. So the first one was also introduced by our colleague the other day. It was Football Project, the Food Biomarker Alliance. So it was an initiative aiming at identifying and quantifying dietary biomarkers in order to improve the capabilities of nutrition assessment and research. It was the first consortium from this initiative. It was 22, I think, institutions where also the University of Alberta was on board, and with all of them aiming to identify some biomarkers of nutrition. One approach was to divide, one of the work package was to divide different groups, focus in to develop a specific interventional study with one food, to try to describe, to analyze which metabolites, which is the metabolic fingerprinting of the specific metabolites after one intervention. It was controlled. We were 6 months defining how this study could be done. So this is not. And we focus in legumes. So we run as the importance to our country. So we focus and we run some studies on these legumes. So the idea was to study from the acute intervention study, some chronic interventions study, and also the real life, that is the observational studies. So this is where this is I'm trying, so being aware that in the first one we have high level control of diet, high number of discriminant metabolites. However, as far as we move to observational studies, we increase the heterogeneity of the population, the inter-individual variability, so the complexity, and being aware that we will not be able to have some 1-2 biomarkers. So when we will, as it was presented the other day, so we will consider multi-metabolites, patterns, or different strategies. So we published this paper also in collaboration with David Wishart, so to try to set up what the food metabolome is. So from diet, from what we are exposed, so we have to be aware that after becomes the digestion, the hot metabolism, the microbial metabolism, that is one variability that we need to focus and to take into account strongly. And also in our samples, we will find food metabolome biomarkers, endogenous biomarkers, drug biomarkers, pollutants metabolome, and for sure, all of them will not be the same that are in the air or in the food. They will be transformed. So, and we need to know which transformations become from all of them, because the complexity is served. So this is just a quick. So considering in polyphenols, so we have that there are flavanthiols, flavonols, anthocyanidins, tyrosols, and all of them has some specific compounds. Flavanthiols, we have epicatechin, catechin. So, and all of them, there are in different. There are not specific of one fruit. There are some that yes. For instance, blackberries are richer in cyanidin glucoside, but blueberries have all the anthocyanidins possible. So this is it's important. So, however, this is one specific thing that we were speaking the other day. After the microbiota metabolism, some of these metabolites are produce similar metabolites. So at the end of the day, if you are studying plant-based diets, it doesn't care if you find epicatechin or valerolactone that comes from microbiota, because it will be that is to highlight the importance of these microbiota metabolites, because they have longer life, and also they came from different foods, all of them from vegetal, from plant-based metabolites. So, wow. No. Okay, this is just as an example of the football was a big consortium, and also we produce a lot of literature. This is each one of these interventional studies produce. So we produce food biomarkers of apple, pear, biomarkers of coffee, tea. All of this was produced because science, what is written exists, and if not, no. So, and this validation scheme was also presented the other day, and was nowadays there are the same group published in Nature Metabolism one update of this, what biomarkers should be followed. In this, also in this some others papers related just with the how to validate, or trying to how to validate these metabolites. So because we are aware the classification of dietary and health biomarkers within the space formed by three biomarkers, hyper categories: exposure, susceptibility, and effect. So this is something that we have to take into consideration. The next, if we move, the next is MAPLE. MAPLE was a consortium that it was with University of Milan, Ancona, a geriatrician from Ancona, also Norwich from UK, and our group, and it was the microbiome manipulation through polyphenols for managing gut lignins in the elderly. So being aware, our objective was the project was to test the hypothesis that a dietary pattern rich in polyphenols reduce intestinal permeability and decrease inflammatory bacterial factors in the bloodstream, promoting a protective metabolic phenotype in the elderly. So when polyphenol diet is poor, we will observe increase in systematic inflammation. So, however, when and this was the hypothesis, as far as we increase this intervention with polyphenols, they will have an effect in the intestinal permeability, trying to deal with and to keep the integrity of the permeability, and this will repercute in low inflammation. So this we study in different. It was based on one intervention study in older residents, una residencia de ancianos. So it was an intervention with polyphenols, with different kinds of polyphenols. So the coffee, chocolate, apples, some of them, they were distributed, and for several weeks this was the intervention, and we analyzed after each intervention. So it was not easy, but also it was the group of Milan that it was really great. So we some of the lessons learned. So the alterations in the intestinal microbiota were also associated with increased intestinal permeability, and this was frequently observed in older adults. So we, however, so this is the components of the diet are transformed by the intestinal microbiota into metabolites and act on the intestinal microbes in the intestinal epithelium. So we can, from polyphenols, we can think about phenolic acids or propionic or valirolactones, and also, for instance, dietary fibers. And we will see after how the short-chain fatty acids are also involved as they came from fiber digestion. So can dietary intervention restore the intestinal microbiota and reduce intestinal permeability? So yes, so this was what we were testing in our study. So also we focus, do we have enough scientific evidence to be able to define a protective dietary pattern? So, and we review this polyphenol intake and health outcomes, and trying for these questions. So it was, and also it was another systematic review focused in dietary fibers and short fatty acids and gut microbiota composition. So, and we follow the different inclusions criteria, all of the studies that we consider, and being this is the studies where came from in this, and to review, and this is a first approach, and we start to keep going with this hypothesis. So in this, so the next one will be another one focused in neurocognition. So the DECOG Plus. DECOG Plus was a consortium with these universities, Bordeaux, INRA, Amsterdam, and also the King College, and focus in the identification of dietary modulators of cognitive aging and brain plasticity. So we try to discover the dietary bioactive compounds that underline an individual risk and resilience to cognitive impaired risk factors associated with aging. So trying to understand the role of these dietary modulators at the neurobiological level in order to effectively explore the identify protective bioactives. So with this, we work even with in vitro, with rats, and also with human studies. We analyze and we have access to the 3 cities studies. It was an observational study with the aim of examining examining the relationship between vascular disease and dementia in adults over 65 years of age. So this is the described. And it was interesting because we could have access to two independent cohorts. So the Bordeaux, with 2,000 something individuals, and Dijon for nearly 5,000 volunteers. So, and we, with all of this, we proceed with identification on 202 participants with accelerated cognition decline versus and others participants with normal cognitions in the two cohorts. We use different strategies for stratification that it was run for the group of Bordeaux, the group of Cécile Samier. For each case, a control randomly selected with the same age at baseline, same gender and education level. So, from our group, we ran this, we analyzed this target methodology based on our dietary biomarkers, and some metabolites that came from a specific food, they were associated with this prevention or associated with cognitive decline in this 12 years perspective study. So it was the 1-methylxanthine, the caffeine, the trigonelline, the hydroxyprolinbetaine, prolinbetaine, some of them. If we move to the other study, it was Digumet. This Digumet was more focused in the study of the metabotypes. So it was diet and microbiome-based metabotypes for tailoring intervention strategies and promoting healthy aging. It was mainly three groups. It was led by Professor Rikard Lambert from Chalmers University, and also from Naples. And there was also the collaboration of the Danish Cancer Society and Barilla as an industry. So we saw that recent studies suggest that groups of individuals have unique metabolic response to food and dietary change. So we knew that the gut microbiota, which already plays a crucial role in human metabolism, has been shown to underline such health problems. So therefore, the interaction between diet and microbiota can determine the risk of metabolic disease and whether certain dietary change will improve an individual health. With this to cell metabolism that were focused this specific idea, so we start with the hypothesis that individuals with similar metabolic phenotypes, what we call metabotypes, will have similar response to diet. So for that, gut microbiota diet interactions, so we know that are major determinant for specific metabotypes that are linked with cardiometabolic disease risk, and other we move. So our aim was identify unique metabotypes and biomarkers that can guide the personalization of diet intervention for adults at high risk for cardiovascular disease. So from the whole population, according to different or lifestyle, diet, genes, gut microbiota, metabolite groups. So we classify and this molecular phenotyping for cardiovascular risk, and in each group we could proceed with a specific diet. In our case, our specific diet was based on a combination of dietary fibers, that this was. So this is the idea, to move from generalized nutrition to group-based nutrition. So as yesterday, today's hace 2 días. So it was a doctor that explains really brilliant what can metabolomics do in terms of precision nutrition. So, and we need to see which risk of the patients, we can see this advice to individuals group into similar phenotypes. So this metabotyping, we review, it can be a strategy for this personalized nutrition or precision nutrition aimed at disease prevention. So methodology to target inter-individual variability, and we can use potentially this metabotyping for targeting metabolomics and define these metabotypes. So in this study, we work with two kinds of studies. One was observational, so we start from the cancer, from the cancer research in Denmark. They have a big cohort. It's with the next generation. It's 50,000 participants, and from them we select some a group of 500 that we were following with 1 year. So, and with all of them we have the different sample specimen. And in parallel, so the idea was to try to determine some specific microbiota relevant, in this case of Prevotella bacteroides, so that were specific with the fiber, with after to design an interventional study with doing first analysis of this microbiota and after to provide this intervention based on fibers. So with all of them, it's not really well. So when we had different specimens that allow us to have a multi-omics approach. So we, in this, the MAX study, the observational, we work in this, in the definition of plasma metabolic profiles based on plant-based. So, and we define some metabolites that allow us to define what a plant-based diet is, we can consider with different approaches. So, and in another study, we study specifically and we look for markers of this dietary fiber focus and associated with cardiometabolic effect. So with this, this is in the observational study, we had these 600 participants. The description. We draw our metabolic plasma metabolomics, and we study and trying to identify some phenolic acids and phenols derived from gut microbiota. Also, we observed 2 microbial metabolites associated with fiber that were observed in every study time point. As I told you that we followed 3 times over a year, and it was the 2,6-hydroxy benzoic acid and also indole propionic acid. This indole propionic acid is one of the, it has a special relevance. So another, one of the last, because the metabolomic hub was one hub with working together to the development of metabolomic methodologies, but the last one, CarboHealth, was focused in specifically the looking for metabolites, markers, the study of the consumption of 5 rye, in this case interventions, associated with metabolic risk factors. So in this intervention study, so that it was as in this, we are screening and we were following, it was refined wheat versus high fiber rye. So we, in this summarized table, we observed some metabolites that were specific from different parts. For instance, from some associated with rye intake that are in red, some associated that with both, that are in violet, and some from dietary, the whole grain dietary fibers. But we can say also some gut microbiota metabolites like indole propionic are described and were observed. So to move on, in this now this part of the methodology, we will, as we explained before, the three pillars that we are doing now, that how the part of dietary assessment, I will introduce one software what we developed for the calculation of the specific polyphenols of the diet from food frequency questionnaire or dietary records, and also some developments and our ongoing need to improve the methodology, the target methodology that we are using. So in this the software, it has been registered, it's okay, but it provides us the amount of polyphenol compounds on the right side, so we can calculate milligram of polyphenol compounds starting from different kinds of dietary assessment, food frequency questionnaire, 24 hours. So we cross with some food compositions tables on polyphenols that came from USDA that are published, also Phenol Explorer, and also some of our that came from our analysis. So, and we use. However, so when we try to study what happened in an epidemiological studies, so regularly, commonly, to study the diet, we use this dietary assessment information. So, however, we know that there are factors not present in the traditional dietary assessment that interfere and we need to consider. That's why it's so important the use and the combination with validated biomarkers in specimen. So because we know the genetic variability, the lifestyle physiology factors, like all of them, also dietary factors, so the nutrient bioavailability. So as we explained before, soya, the active compounds, it's described to be equal, but there are some individuals that are not equal producers. So as far as they report that they are the intake of soya, they will not produce the active compound. So it's important. So as all of you, and after 1 week, we know the importance of biomarkers. So it's just to highlight this part. So one example that we published in the Inchianti study, so to compare how we can obtain from dietary biomarkers and biological biomarkers, is that what we analyze from the urine, from the plasma. So we saw the high concentration of urinary biomarkers of polyphenols intakes were associated with decrease in mortality in older adults. But always, no. So we have here the comparison, and we on the right side we can so in all of them we relate the total polyphenol with total mortality. In one place it was on the right from data from dietary intake, and on the left part data from the urine biomarker. So we were able to observe a 30% reduction when we consider this biomarker, these polyphenols biomarkers, was analyzed from the urine. So, however, combination is fine. So, on the next step is the methodology. So we we in Barcelona, so we work on this methodology. So we develop one methodology to analyze food-derived metabolites, endogenous metabolites, microbiota-derived metabolites, and environmental contaminants. So that this methodology we apply to all of the projects that I previously described. So this methodology was able to analyze 1,090 metabolites using low sample volume, short run times, and we able to theoretically see 500 endogenous metabolites, 450 food-related metabolites, pollutants, biomarkers of lifestyle, and microbiota-derived metabolites. This was a nice paper. It was recognized by one of the best of the American Chemical Society in the Journal of Food Chemistry Research. So, however, we as a scientist, we always know that we need to improve, and it's important to know our drawbacks. So, and to know how we can keep going to improve, and to, in order to, in our case, to try to apply this methodology to a big cohorts, a large observational studies or large interventions. So observational because it's the real lives. So we need to keep going increasing. So for this, we move to a 600 Q trap to a 700 Q trap. So we increase the number of metabolites that we were able to identify based on we increase the tryptophan pathways, isocyanates, curenines, glucosinolates, flavonoids, indole derivatives, and resorcinol and derivatives. The resorcinols are markers of fiber intake. We increase our limits of quantification in some of the compounds, obviously. However, as we say, we need to keep going to improve. We need to learn from the best. So, and for that, after pandemia, so I decided to move to Canada. I asked, so I was really grateful to the Wishart Lab, and they host me, and we try to work together in several items to what we can offer both groups the best as we can do and improve. So this is the view from my desk. So, and we cover the different. It's a really nice city, Edmonton. Don't believe those that say that it's too cold. It's too cold if you don't have the right people. So okay. So some of the Tammy Allen also came to Barcelona as we did, and we also work in the application of the MEGA in our lab. However, one of the aims was also to keep going, improving. As I start my presentation speaking about the importance of the exposome. So not just to air pollutants, that also, not just plastic, that also, but all of them, and also including some important dietary biomarkers that we choose according to what we observed that they were identified in our previous studies. So in our previous studies, we knew the quantification or the presence of these markers. So with all of this information, we try in a collaborative work to develop a new exposome assay. That this has been and is being developed in the Wishart's lab. So this exposome here is the 1.0, but I know that there are other. This needs to be updated. They have some specific compounds that let us to catch up all this is the idea, what we can use in the exposome studies. So what the compounds classes are these and the examples of all of them. It's just to show you, I wanted to show that this is an important also assay that is, because it's really important to work with these validated assays. So, because the idea is to use this, all of these markers to explore, to deep study the different health status, not just the health, the illness, but as they say before, what happened before, what we can do before to try to prevent. Because I came from a nutritional department, so we are, when the illness arrives, is the role of the doctors, but we have a lot of room for improvement to work 10 years before. So, and this is the importance of this, to study these big cohorts. This is a slide that Dr. Jamile Lopez shared with me, that considering all of these metabolites and the idea to cross with all the different health status. So this is one, and these biomarkers, as far as they are robust, they will help us and also to study in deep way. So, and we are also, nowadays we are working in classifying, crossing by the literature, which markers are already published with each specific illness. So this is important research that Dr. Jamile Lopez and also our lab, we are working together. And to finalize is, obviously, we are happy because we have challenges and opportunities. So with this, I will be very, very brief. I just share with you, there is this paper in Science Advance, the Metabolomics of human aging, advantages, challenges, and opportunities. And it's a very nice and interesting paper because they review all of the studies that consider metabolomics and studies in aging, and we can see that according to the years, that from 2005 to 2020, so how the techniques has been developing, and also the number of participants is in a logarithmic scale. So nowadays we are moving, that triangle is the mass spec, so the most of them, the NMR was the square. We can say that at the beginning there was mainly NMR, but nowadays they are using more and more the mass spectrometry for this quantitative approach. On the right side, there is a table. For that, I invite you to and we can share the paper, because it's interesting to see that the most of them, when it's a target, they quantify 200 metabolites, 100 metabolites, no a big number of metabolites. There are a big features when there is an on-target, but not when it's quantification. So it's very, very interesting. This is the where came on the right side, where came the metabolites in different countries, and also which metabolites are related with different organs. So the amino acids, the lipids, and say if they are positive or negative association with this. I will recommend you this as a open mind. And this is the last two slides, that this is our ongoing project. We are focused what we call food for brain. Now during this week, we also got a specific grant to study a similar, in this case, food for brain study, where also the Wisha lab collaborate, is to study the exposome and biomarkers associated to brain health. So this is an initiative, this is a cohort in Barcelona. And its focus, I think that is really challenging because it's focused in the study of 7 pillars, group in brain health, cognitive research, and brain plasticity. So the clinicians have been running on all these different biochemical and also NMRI, so to study the brain health, and focus in these 7 pillars that are really interesting: cognitive training, physical exercise, nutrition, life plan, comprehensive health, socialization, and sleep. This life plan I really like. So because how important in this cohort is they have a lot of data from them, and also this vital plan, how important it is. And also, obviously it start, maybe 5-6 years ago, and it was the pandemic in the middle, and it was a follow-up. Obviously, the pandemic was not organized to study these items. However, the clinicians use, and it was in the middle of the pandemic, so they used to use their variables, the items, to study the importance, for instance, from the resilience. What have those individuals that had a better improvement in different health status? So this is just for these conclusions. So is the exposome consent strives to capture the diverse and range of exposures, including synthetic chemicals, dietary components, physiological stressors, physical factors, as well as their corresponding biological response. Addressing exposome requires a joint international effort, as well as a strong motivation for collaborate. So this is very, very important. Precision nutrition approach includes, in addition to genetics, other factors such as dietary habits, eating behavior, physical activity, microbiota, and metabolome. So this revolutionary vision lies in systems thinking. It's necessary to understand the complexity of all kinds of dynamics process in the organism as a whole, in a holistic way. So with this is my slide. Thank you, all of you, for your attention. I'm happy to answer now or later any question that we have, because there are hope for the improvement. Thank you to all of you. In Spanish, for sure that we have words.
In fact, although I didn't say you are one of the most enthusiastic, intense, active, and really, really good person I have ever known. So, my pleasure.
But you are in the. I admit that you are in the ranking, in the top one. Yeah. So this is it's.
Time to some questions for Cristina. She's an expert. I hope you.
Hola, voy a hacer la pregunta en español, creo que es más sencillo.
Perfecto.
A mí me llamó mucho la atención estos metabotipos. ¿Crees que sea posible poder tener como un consenso de los metabotipos independientemente de dónde provenga la muestra? Y si va a ser posible tener como una firma de biomarcadores para diferentes enfermedades, incluidas las que están asociadas con el envejecimiento.
La segunda, firma de biomarcadores por enfermedad. Sí, es lo que se está haciendo, que se está intentando. Ahora hay que hacer un gran esfuerzo en cruzar con la literatura que está escrita. Y esto es text mining o hay que usar las bases de datos. Sí, o sea, todos estos biomarcadores, al final hay muchísima bibliografía y se está intentando relacionar con diferentes. Y la que tú dices de metabotipos, la idea es partir de cortes y ver observaciones. O sea, por ejemplo, la que he explicado de la ingesta de fibra, habrá diferentes metabotipos, dependiendo de diferentes... el metabotipo es un concepto que lo puedes tomar de muchas maneras. Al final es hacer clústeres, es hacer grupos. ¿Y cómo los haces? Entonces, como el juego, ahora los que lleven la camiseta amarilla a la derecha, ahora los que lleven, o sea, podemos ir haciendo. En esto, nosotros en el de fibra, pues vimos que el consumo de fibra a todos no iba, pero si seleccionabas un gen que está descrito, asociado con un declive cognitivo, pues entonces en esta población sí que tenía.
Es que justo mi pregunta va en sentido de que cada población, cada cohorte, tiene diferentes estilos de vida, diferentes, digamos, comidas tradicionales, entonces podría estar como un poco sesgado. ¿Qué tan sencillo sería realizar este grupo de estos metabotipos?
Claro, porque tú dices comidas diferentes, pero como el otro día explicaban, que está la iniciativa de la tabla periódica, o sea, todavía no conocemos la composición de los alimentos, pero lo que más caracteriza a los alimentos, muchos de ellos son compuestos bioactivos, porque las proteínas las tenemos en el cuerpo, los lípidos los tenemos en el cuerpo, o sea, lo único que sabemos que viene de fuera son vitaminas, porque viene por definición, y luego los compuestos bioactivos, y que no es poco, porque eso nos caracteriza del lugar donde estamos. Entonces, los compuestos fenólicos que puede haber en el mango, en la papaya, también están en la naranja o en la pera. Entonces, que tampoco diferimos mucho, o sea, sí que hay comidas, aquí pueden haber, pero que es importante es desarrollar, y aquí tienen ustedes mucho rango, la importancia de desarrollar buenos métodos, como los que se han presentado aquí, para luego aplicarlo a las cortes de diferente país. Hemos visto la cantidad de cortes que hay para para ser analizadas. Y entonces nosotros hemos determinado en un estudio pues, un patrón dietético asociado a plantas. Esto, una vez está, y nos han pedido el approach que hemos hecho estadístico para aplicarlo en otro estudio. Por lo tanto, yo creo que por eso decimos tanta la colaboración, porque es importantísimo. Cada país, cierto que tiene sus reglas, pero no somos especiales, la genética, pero bueno, tampoco somos, es asumible.
Muchas gracias, felicidades por el trabajo, está muy bonito.
Yo tenía la duda, ¿han estudiado el nutrimetaboloma de centenarios? Porque ciertamente, como dice el autor, es diferente. Hay gente centenaria en Japón que tiene un healthy aging y tiene un exposoma muy diferente al de, por ejemplo, en Costa Rica, en la zona rural, que también es centenaria. Entonces, no sé si han estudiado en centenarios o en supercentenarios. Esa era mi primera pregunta. Y la segunda, si han intentado relacionar algo del metaboloma con el reloj epigenético, porque ciertamente ustedes tienen como patrones que parece que hay como algo, decía, del acelerado, el envejecimiento acelerado, a lo mejor podría tener alguna correlación con el reloj epigenético.
No, ciertamente, la parte de epigenética es importantísimo, nosotros estamos intentando hacer estudios multiómicos donde está la parte genética, pero también la epigenética, porque también es importante. Nosotros, en algún estudio de estos consorcios, por ejemplo en Digumet, tenemos diferentes ómicas. Y entonces, pues ahí se está trabajando y sí, porque los cambios, la epigenética es también muy activa. Analizar a los centenarios and ultracentenarios, they are the Champions League, so they are really good. Y hablando con los geriatras, ellos dicen, a los que realmente el concepto es una cosa que nosotros hemos aprendido y que es bueno y me gustaría compartir aquí. El elderly, estuve hace un mes en la Sociedad Española de Geriatría, ahí con todos los geriatras. Ellos no quieren hablar de elderly de menos de 75. Not so adults up to 75. No me dirás que no es bueno esto es fantástico. ¿No? O sea, pero porque ellos dicen, realmente somos geriatras y empezamos a trabajar, o sea, nuestra especialidad es a partir de los 80. Porque antes, primero porque han mejorado las condiciones y todo, pero antes hay que hacer esta criba de pues de enfermedades mundanales, que podemos decir, y los digo con la empatía de decir, pues los cánceres, el cardiovascular, a partir de 80 y pico es donde se empiezan a ser, y son totalmente diferentes y muy bien. Nosotros iniciamos un proyecto Over 85, que estoy súper emocionada de estudiarlos, porque ahí sí que se pueden ver importantes. Vamos también a estudiar telómeros, o sea, para ver, porque sí, realmente son diferentes, son los de Japón y son los que realmente podemos ver el healthy aging en esto. El healthy aging mejor, better, over 85, because we have a lot of learn from them, not just, obviously, in a conversation, but analyzing their biomarkers.
Hola, doctora, buenos días. Excelente plática, gracias. ¿Han estudiado alguna relación de pacientes, ya hablando de, pacientes con tratamiento con polifarmacia? La metabolómica que existe en polifarmacia y si cambia con respecto a una dieta, por ejemplo, una mejora en la dieta.
Por supuesto que el polifarmacia le hemos de estudiar, lo vemos. Cuando yo he explicado los markers que vemos, están todo el grupo de los drugs, porque los estamos viendo. Entonces, podemos determinar los metabolitos que se están tomando. Los hemos incluido como estándares, que de hecho me llamó la atención mi rector para decir, ¿qué estás comprando, Cristina? O sea, ¿qué estándares estás comprando? Porque compramos todas las drogas más fancy. Entonces, estáis haciendo un festival en vuestro laboratorio, porque enseguida saltaron las alarmas, pero los hemos de identificar para poder incluir en la metodología. Y estudiando adultos mayores, que es lo que, obviamente, la polifarmacia está servida. La usamos como variable, o sea, hay que tenerla en cuenta.
Pero sí existe una mejora, por ejemplo, el decline del estado cognitivo de los adultos mayores. Si usted, por ejemplo, tiene polifarmacia y mejora la dieta, ¿pueden mejorar ese decline, por ejemplo?
A ver, hay que ir con cuidado con la farmacia, porque entonces en algunos estudios depende de qué estén tomando, obviamente es un criterio de exclusión. Si tú estás viendo el declive cognitivo y estás tomando según qué fármacos, o sea, es una variable que hay que tener muy en cuenta, o la analizamos, la tenemos en cuenta, dependiendo pero que la polifarmacia hay que tenerla en cuenta, porque ya podemos estudiar el efecto del betaglucano, que como esté tomando un anticolesterol, un esterol oportuno, así como un danacol, estos compuestos que a partir de la dieta están dichos que te bajan el colesterol, pero claro, como la persona te esté tomando un fármaco anticolesterol, te lo baja, no hay color, hay que tenerlo en cuenta.
Gracias.
Gracias, doctora, muy interesante su trabajo, felicidades. Solo por curiosidad, ¿cómo se relaciona todo esto con la ingesta calórica? O sea, no solo obviamente con la diversidad de los alimentos, pero con la ingesta calórica, ¿qué han visto relacionado a eso?
A ver, hay dos partes. Una, la parte calórica, la energía, siempre es una variable que hay que ajustarla y si no la tienes no puedes seguir. O sea, esto es una variable, la tenemos en cuenta de esta manera. Luego, por otra parte, es que se hayan hecho, no he participado directamente, pero se están haciendo estudios del ayuno intermitente, pero esto ya es como otro capítulo. Obviamente es una variable que si no la tienes no hay que ajustar por ella. Si no, es como con la orina, que has de normalizarla. Utilizar la metabolómica en este concepto. A ver, yo creo que la conferencia que nos dio el médico el otro día fue excepcional, porque realmente nos hablaba de la nutrición de precisión y ver, cuando digo la nutrimetabolómica, estoy hablando de los marcadores que estamos observando. Y nos presentó nos habló, ahora no sé si era un Lancet del octubre del 2013 o así, que decía la importancia en prevenir, en crear marcadores de riesgo, en usar la metabolómica para el diagnóstico. Lo hablamos, o sea, nunca tendremos, siempre será más barato sacar un centímetro y medirle la barriga a la persona. O sea, es que no tenemos competición. Para diagnóstico no lo vamos a hacer, pero hay 10 años antes poder establecer, y para esto, en práctica translacional, mi opinión es lo que creo que es que vamos a ir por ahí. Bueno, el Lancet lo explicaron y gente mucho más erudita, de decir, podremos con biomarcadores, cuanto más amplio, cuanto más sea el abordaje de los biomarcadores, más podremos determinar y podremos determinar grupos de biomarcadores que nos predigan el riesgo de determinadas enfermedades. Y ahí están los estudios. O sea, nosotros acabamos de tener un estudio con cáncer de próstata que teníamos, no lo he puesto, pero teníamos las personas al inicio, al baseline, cuando todo el mundo era sano, y luego se han seguido durante años y ha habido incidencia de cánceres de próstata en este caso. Nosotros estudiamos los basales cuando son sanos, sabiendo lo que pasa e intentando ver qué tienen los sanos que les permite continuar siendo sanos. O sea, y la gracia, el gran espectro es estudiar población sana, o sea, para ver y hacer seguimiento, y actualmente se ha visto, hay mucha cohorte, y ustedes aquí también tienen, en Latinoamérica, tienen mucha cohorte, mucho estudio, y que vale la pena identificar biomarcadores, porque now the methodology is ready to analyze these markers. Y para ver risk prevention, metabolites, patterns, to predict the illness, because is what this represent a huge save of money. I don't know, but I think that each euro or each euro in prevention is an enormous save in the treatment. If you compare with the treatment, so this is important.
Bueno, muchas gracias por la presentación. Voy a hacer la pregunta en inglés para también tener un poco la opinión de Dr. Richard. So thank you very much for the presentation. It was pretty nice. I will go a little bit forward, and I want to know your opinion. How is the connection? Moreover, know about. Okay, we are scientists, we really like to enjoy the research, the results, but all of we do is connected to the policy makers, the government, the implementation of plan, something like that. How is connected, how close are the government in Barcelona, in Spain, in Europe, with your results, with your projects, are already supporting. They are really interested, or they don't want to know anything at all. And the same maybe in Canada, how is the situation, the political situation connected with all your programs?
Good question. Because at the end, we are public, so we are working with the money of all. So we need to be useful. For that, if we want to as far as in my opinion, and this is what of this kind of workshops are important. Try to validate technologies, how to validate, because in industry, in the real life, without validations, just with the fancy methods of from academia, we will not do anything. So we need this kind of a standardization, validation, accreditation in the clinicians to try to translate. This is one point. And other, for instance, in Europe and maybe here, so there are some specific goals that to follow up the research and to say, okay, now, but I will give you, I will will say, million of euros or whatever, if you translate and if you connect with industries. And nowadays, they are increasing, and the input of the industries in an fair environment, in an open science environment, because if we use public money, we need to be open. But well, at the end of the day, there are some agreements, everything has to be clear. But yes, there are some specific goals and projects, not just based on basic research, trying to translate to society, to public health, to be useful for citizens, for the associations of citizens. They are there. Nowadays, there are no European projects without any, if you don't consider the Patients Association. So, because we have to be useful for our society. And for this, working in a validated, in a standardized framework is vital.
One question more. Yeah.
Voluntarios que la actividad física, vale, sí, yo no tengo directamente un estudio directamente con actividad física solo. No, miento, es cierto. Lo hicimos en el hospital, en el Gregorio Marañón en Madrid, pero eran con personas mayores. Y lo que se veía es a una igualdad to the same diet. We classify in two groups. One, helping with some kind of physical activity. That means, I don't know, say sentadillas. So it was with people with 80 and more. So in the hospitals, they are trying to implement some initiatives to implement this physical activity and it was really an improve this kind of initiatives. In healthy, in the others, it's just a variable that we consider the rate of the physical activity.
Okay, now I invite you just to take a break, grab some coffee, some tea outside, and we will have 15 minutes, more or less, to be here again for Dr. David Wishart conference. So. Distinguished university professor in the Department of Biological Science and the Department of Computing Science at the University of Alberta. In 2011, Dr. Wishart founded the Metabolomics Innovation Center, which is the Canadian National Metabolomics Laboratory. Dr. Wishart and his colleagues have identified or found evidence for more than thousands of metabolites in the human body. This information has been archived on a freely accessible web resource called the Human Metabolome Database. More recently, Dr. Wishart's efforts have focused on characterizing the content of various food and food products, including milk, dairy products, eggs, meats, herbs, spices, fruits, vegetables. This information is now available in a resource called Food Database. Also, Dr. Wishart probably will talk about some other databases he has created across the years. Dr. Wishart has published more than 400 research papers in high-profile journals on a wide variety of subject areas. Dr. Wishart, as I said previously, doesn't need introduction in the field of metabolomics, and as I also said, is an inspirative source for all of people, young people, researchers, and all the community working with mass spectrometry and metabolomics. So, Dr. Wishart, welcome, and the floor is yours.
Thank you very much, Emione. It is a pleasure to be here. It's great to see many of the workshop participants back again for our final day, but also many new attendees listening to this conference and the meeting. So I know that I'm scheduled to speak for 2 hours. So what we're going to do, at least, I'm not sure how long this will end up being, but we'll break about halfway through for maybe 5 minutes just for people to stretch, or if they have to go to the bathroom, or for me to rest my voice. So today I'm going to be talking about how to make metabolomics matter. I think, this year, or maybe it's last year, although we can't really be sure, but metabolomics is a quarter century old. It's 25 years. The first paper that mentioned the term metabolomics or metabonomics was published in 1998. So it's grown. There are thousands of people doing metabolomics in about 80% of the world's countries. There's thousands of papers that are published now every year. There are companies that are producing metabolomics tools, equipment, supplies, reagents, and kits. And in fact, the market for metabolomics seems to be growing very quickly, about 12 to 15% per year. And in the next 5 or 6 years, it'll be worth up to $7 billion US. So if you look at publications in or on metabolomics, you can see how it started in 1998 and has been growing steadily. So there's, as of 2023, there are almost 14,000 papers published on the subject of metabolomics. But I think a question for all of us is where is it going? Is it going to continue climbing as it has, or it's starting to level out, and is it going to sort of flatten, or have we reached the peak in terms of metabolomics and its impact, and now it's on its way down? I think those are important questions, especially if we want to make metabolomics relevant, how to make it matter. So, will metabolomics go the way that MS-based proteomics has gone? Now, it may be different here in Mexico, but in Canada and the US, many of the MS proteomics core facilities are closing. They're winding down or getting smaller.
And a lot of those instruments have been replaced by tools, services offered by other types of companies that use either antibodies or hybrid sequencing methods or electronic measurement systems. And the reason why that happened is because these new technologies are quantitative. They're also cheaper. So that's sort of been the fate for MS-based proteomics. Can metabolomics keep on growing up? And this is what's continued with genomics. It just keeps on growing. It keeps on becoming more visible. Another question is, will metabolomics change your health? Will it increase your lifespan or quality of life? Are there going to be, and have there been, breakthrough discoveries with metabolomics? Things that hit the front page of newspapers or announced on TV, or where presidents and prime ministers have news conferences about those developments? Will metabolomics become part of precision nutrition and part of precision health? Or will it just be the domain of genomics? So I think there are some important bottlenecks that are limiting metabolomics from reaching its promise, or for metabolomics to really matter. And that's actually going to be the focus of my talk today, is how we can clear some of those bottlenecks. And this was brought up by Yamila in her early presentation this past week. So there's many issues, but these are maybe 6 or 7 that I think are really important. So in metabolomics, we don't have good standardization. In metabolomics, we don't do quantification. We don't really have a lot of automation. Costs for analyzing samples is actually quite high. The number of compounds we typically measure is actually quite small, and only a tiny portion of what's known. The equipment we have is quite big, it's expensive, it costs governments a lot of money for us to do our research. And over the last 25 years, we've been challenged with translating our findings into the clinic or into practice. So what I'm going to do is I'll talk about these, I'll frame them so that you have a better understanding of where the challenges are, but I'll also talk about some solutions. Some of them are being developed in our lab, some of you already have tried, some are being developed by other groups around the world. But I want to use this time to open your eyes and your mind about how you can help change things, how you can make metabolomics matter. So most of you weren't involved in metabolomics in the early days. I was, and there's a lot of excitement when the field emerged with various workshops and meetings from scientists around the world trying to create specific standards, trying to develop tools and methods to share data, to report data, to standardize how we do experiments. An initiative called the Metabolomics Standards Initiative, MSI, was formed. It met regularly. They published papers that gave consensus agreements, standards, database ideas, and database concept that they wanted everyone to use. And it was exciting at that time because we wanted to correct the problems of the past, where too many things were being done by different people in little silos or rooms. But this is what happened. So you can see this already. So there is a database called Metabolites, which is based in Europe, and there's a database called Metabolomics Workbench, which is in the US. They use very different formats, and they were designed only to capture the data on studies, which is helpful, but when you have a field where everyone's struggling to identify compounds, we're not really interested in the studies, we'd like to have some reference databases so we could identify compounds. So separately from those national initiatives, individual labs started creating their own databases for reference data with spectra for pure compounds. So GNPS emerged, MassBank emerged, Metlin emerged, the Human Database emerged, and many others. Yet each of those databases also is different. Some are specific to NMR, some only use or capture MS data, some do it for pure compounds, some do it for mixtures, some focus on, say, retention time or collision cross-section, each of them collecting different types of data in different formats. Even with the establishment of metabolites and the metabolomics workbench, only a tiny fraction, less than 5% of metabolomics studies are having their data deposited into these databases. Likewise, these standards databases, most of them don't support deposition or don't do it in a standardized way. So it's a bit of a mess. It's also a bit of a mess when it comes to things like naming compounds. These are all the names or identifiers that are used just for alanine, and there's many more. But if you were to think about some more complex compounds like 1-methylhistidine and 3-methylhistidine, where those names have been switched at least 3 separate times over the last 4 decades, so that almost no one knows which one is 1-methylhistidine or 3-methylhistidine. And it happens over and over again where someone thinks they've discovered a new metabolite, but it was actually discovered 30 years ago, but it's always been named differently. This is a confusion that plagues metabolomics. There's no consensus about how to formally identify compounds. The Metabolomics Standards Initiative came out with a pyramid, level 1, level 2, level 3, level 4. Some of you who were at the workshop remember me describing this. That came out 17 years ago. 10 years ago, Emma Szymanski developed a different scale, and it has 5 levels, and it's an inverted pyramid. Some people use the Szymanski scale, some use the MSI, but both scales are developed specifically for MS. Yet a lot of people do NMR metabolomics, my lab. Others will do GCMS metabolomics. Some will do infrared. Some are doing electron or X-ray crystallography. And so these scales weren't really made for those researchers. There's also no consensus about how to do metabolomics. Should it be targeted? Should it be untargeted? Should it be quantitative? Should it be relative or non-quantitative? Targeted or non-targeted is specific to high-resolution mass spec, whereas targeted allows you to basically apply it to all platforms, GCMS, LCMS, NMR. So this is, again, a challenge, and likewise, there's no standard method for doing any of these. Every lab that does untargeted has its own preference, and many labs that do targeted metabolomics also have their own method or model. So, what should the community do? So for one, if we want to be able to improve the deposition and make things more accessible, we should make data deposition easier. We should make databases talk to each other so that they aren't in separate rooms or silos. We also need to create sort of tools or the equivalent of the Rosetta Stone to help us translate the different names and identifiers for compounds so that we have consistent naming and identification. One way might be to create an IUPAC name translator. You can use these, you can buy these from certain companies, but they're very expensive. The other approach to try and make compound identification more consistent is to toss out the old MSI or Szymanski scales and move to a probability-based approach, which would be independent of the method or platform. I think I've advocated for this, and you guys have sort of in the workshop experienced this, but what we do need to do is to move towards standardized protocols in metabolomics, and ideally these should be standardized quantitative protocols. So I'll talk about how some of these things we're working on. We're not the only ones. In some cases we're working with many other scientists. So those of you who used LC AutoFit were used to dragging and dropping data files. And more, if you do things on the web or if you're filling out forms or registering for a conference, you drag and drop a file in. That's a lot easier than sort of fill in your file name, decide on which format it is, then being told that the format's wrong, and then going back again. What you do with drag and drop deposition is you put the onus on the computer. The computer has to figure things out. It has to figure out what format it's reading. It also has to figure out how to parse the format. And there are lots of smart tools that allow you to read text, to pull out the metadata, to read formats like NMR-ML for NMR, MZML. And so this is what was done for a database called the Natural Products Magnetic Resonance Database. It took us more than 1.5 years to develop the drag and drop interface. If we just used the simple approach of uploading, it took us 1 day. So it put the work on the programmers, but it's made it very, very easy. So now people can drag and drop their NMR reference data or their NMR mixture data in just a few seconds. The tool is smart, it's fast. Things that they deposit, you don't have to annotate. The computer annotates things. It goes and searches through databases. It checks your data for you. It corrects your data for you. It writes out specific information describing the compound, classifying the compound, making other relevant predictions, telling you what the compound does. All of that's using natural language processing. Next year, the NPMRD is going to be starting to take in mass spec data. And it will be including not just natural products, it will include biological products, because we are natural products, and we produce natural products too, and so do mice and rats and other things. The other thing that we're required to do with this database is that we have to exchange our data with other existing platforms like GNPS and HMDB and FoodDB. So now we're starting to talk to the different databases and connect them. So a description of that deposition form was published in the Journal of Natural Products, but we think this could be a very good model for other metabolomics databases, or in fact, maybe the NPMRD, which probably won't be a magnetic resonance database. It'll be more like the Natural Products and Metabolomics resource database. Another area where there's a problem, and this is something we see in natural products from plants, it's also something we see with humans and with food, and the papers that are published about those, that there's usually confusion about how to name things. And this was described in a paper we published last year about trying to create a way of having or overcoming inconsistent metabolite recommendation nomenclature. We're part of a committee now, and one of the objectives that's coming out of that committee is to create a universal, free chemical translation service that converts a structure that you draw, that you may have determined by NMR or mass spec or someone's told you it. It'll convert it to its common name. It'll give an accurate, correct IUPAC name, and it will generate the INCHI, SMILES, and HMDB, or Natural Products Magnetic Resonance Database identifiers. Potentially also give you the PubChem identifiers. We've also been working to track name and nomenclature changes that have happened over the last 30 years for different compounds, and to describe them in the description sections of HMDB and NPMRDB. We're also working to use text mining and natural language processing to identify synonyms, other names, in some cases other names from other languages for these compounds. So with luck, this will be available as a web service to the community in early 2025. Now the other thing I talked about was the MSI nomenclature, or level 1, level 2, level 3 approach to annotation. There's a universal consensus that this isn't working. No one really ascribes level 1, level 2 numbers to their data. because it's a qualitative thing. If you can make annotation a quantitative thing, where there's a defined number that comes out of it, that gives you some level of assurance, it would be much more objective, much easier to do. So the concept here is very simple, and this is something that Tom Metz, a collaborator of ours in the Pacific Northwest National Lab, has proposed, but with many other scientists, prominent metabolomics researchers who are advocating for this idea. So the idea that you would say that identification is 1 over n, where n is the number of compounds in a reference database. So that could be HMDB, it could be a natural products database, it could be the Metlin database, it could be the KEGG database. But as long as you've told us which database you've chosen, then it essentially gives you some score. And so these are some of the probability values for different database sizes, ranging from 1,000 to 5,000 to 10,000 to a full database of about 50,000 compounds. This is a way of describing, I think, in pictures, which is, I think, maybe more informative. So suppose you just had an MS value, M over Z, or just a retention time. How many compounds would have that same M over Z value or that same retention time? Well, in fact, there'd be dozens that would probably have it. In this case, the example here is the compound of interest is 4-amino-2-methylene butanoic acid. And in this case, we had 9 matches, which with this retention time. So our probability of this compound being correct is 1 out of 9, or 0.11. If we included, let's say, the collision cross-section or drift time with that, that adds a bit more information, and instead of just being this linear picture that's shown here, now it's spread out over 2 dimensions. That's retention time and drift time. And so the number of compounds is smaller. It's 1 out of 7. If we include information, let's say, the MSMS spectra, now, and combine that with retention time and drift time, there's only 1 compound that fits all of those. So the probability is now 100%. So that's a simple way of thinking about it, but it's really the more data you have confirming the identity of your compound, and it could be mass spec, NMR, collision cross-section, it helps validate what's there. Now, not every database has that kind of data, but what we're doing more and more is creating in silico databases that have this data predicted, and it's quite accurately predicted. So I'll explain that a little later on. The last one I think was about which platform, which method, which protocol. There's room for both. There's room for untargeted, there's room for targeted. But the targeted approach is the only one that can meet ISO standards. It's the only one that can give you fair, compliant data. And so as a community, we do have to move towards targeted and quantitative data. And it's, I say, not only is it standardized, it also works for all platforms. It's not specific to high-resolution mass spec, which then becomes exclusionary. So I've put in many of my, at the end of each of these little sections I'll talk about, is what my aspirational goals would be. So standardization, it really matters. It's important. It'll allow us to move our discoveries in the lab into the clinic, into practice, into industry, and into environmental testing, into food and nutrition. But as a community, we need to be able to start doing what, say, the genomics community already does, where about 90% of people deposit into existing databases, not 10%, not 5%. We need to be able to exchange our data so that we can have essentially the same data no matter which database we like or prefer or use. So that data exchange has to be done, and I hope this will be done in the next 2 years. We need to assign confidence scores to the metabolites that we identify Now, in the case of the quantitative metabolomics methods you guys learned about in the workshop, you can write 1.00. If you're doing untargeted metabolomics, when you produce your list of identified metabolites, put a probability number beside it. Don't say level 1, level 2, level 3. We also need to move towards International Standards Organization, or ISO, standardized quantitative data collection and measurement. And this is what's been done in genomics, and that's the reason why genomics keeps on growing, that they are largely ISO compliant. They have standardized things. It's very reproducible. So that issue of quantification is another one that I'll focus on a bit more, because this is really key to the success or failure of metabolomics. So those of you who were at the workshop saw these graphs before. Those of you who weren't, it's just showing a time trend. So from 10 or 11 years ago, a number of papers that were focused on targeted metabolomics and untargeted, and the number or percentage of papers that were quantitative. So in fact, most papers 10 or 11 years ago were on targeted. Not many, but about 1/6 were on quantitative. But the trend has been disturbing. So as of last year, untargeted is vastly more popular, more published. That also means that the proportion of actual quantitative metabolomics assays has dropped and dropped and dropped, and it's now down to 7%. That's very bad news for metabolomics, and it would certainly trend metabolomics in terms of its reception on the downward path. We need to change that. And this has been something that has been brought up 10 years ago in a paper. The title, which might be a little hard, but there's "A specter or a ghost is haunting metabolomics, the ghost or specter of quantification." And it's this fact that even back then, they noticed that more than 90% of published papers are non-quantitative. Fewer than 10% of published papers use absolute quantification. But if we want the field to be robust, if we want it to be reproducible, if we want to share or use universal values, if we want it to be able to compare across platforms from GCMS to LCMS to NMR, if we want it to be fair, compliant, findable, accessible, interoperable, reusable, and translatable to the clinic, we have to do quantification. So there's several options that are open to the community now to do quantitative metabolomics. You can buy kits, you can buy tools or software. You can also get a hold of community-developed kits or tools as well. You can also make your own systems and run those within your lab. You can also send samples to core labs that have the equipment and software to do the absolute quantification. So there's many options. And there are many platforms. There are tools like the food screener and IVX method that Brooker offers for NMR-based quantification. For a number of years, SciEx offered a system called the lipidizer, which was an amazing tool, although it's not offered anymore. There's a software company in Canada that also does quantitation using NMR, just software. There's Biocrities, which offers a variety of automated kits for commercial quantitative metabolomics. And quantitative metabolomics is getting better. In the early days, where most studies were NMR-based, people were happy to quantify maybe 50 to 75 compounds. With Biocrities, when they released their P180 kit, you could measure about 180 compounds. About 5 years ago, they released something called the Quant 500, and you can measure 630 compounds. A new one just came out last year, at the end of last year. It's called the Quant 500, and it measures about 1,000 compounds. Most of them are lipids, but it's still a big number. And then the lipidizer, which is released by SciEx, you can measure about 1,100 lipids. But these are pretty expensive. So if you're buying kits from Biocrities, they range from $4,000 to $12,000 US. If you get the software from Genomics, it might be about $2,000 a year. If you're buying the mass spec instrument, it would also, or buying the NMR instrument from Brooker, those are also hundreds of thousands of dollars. But there are these community tools that are out there. They're software. There's tools like Basil, Batman, GC AutoFit, and Magnet, a number of which we've published on, that are free, and they allow you to do quantitative metabolomics. They aren't as robust as the commercial kits, and they probably need some tweaking, but they are out there, and they allow you to do quantitative metabolomics. More recently, we found that people don't follow the rules or requirements for doing quantitative metabolomics with the software that we produce. So we found it was better to actually make a kit, because then people would follow the directions better. So one example is called Magnet. And the kit has all of the reagents, the instructions, the link to the Magnet software. And this one allows you to do all of the NMR automatically. It does phasing, referencing, baseline correction. It does peak identification. It does metabolite quantification. It does spectral deconvolution. On the web server, it takes about 7 minutes to analyze, but we can run it in parallel. So if you upload 7 spectra, the net effect is all 7 would be done in 7 minutes. So that's about 1 minute per spectrum. It typically detects and quantifies about 55 to 65 metabolites in serum or plasma, up to about 80 compounds in stool or fecal extracts, and around 70 or 75 compounds in wine, in beer, about 60 compounds in milk. So it works, and it's very simple and very quantitative. We've also been working on one for GCMS. It's been piloted in a few different studies and labs. Again, it's a kit-based system because you need specific reagents and a specific protocol, but you also need the software. The software is called GC AutoFit. And you would have a bunch of standards. It would have the derivatization reagents, and it follows mostly ISO protocols. The software I mentioned is GC AutoFit. It's very fast, much faster than LCMS. It accepts a variety of different formats. And with this approach, you can measure up to 115 compounds. So more compounds than NMR, generally faster. This is not quite ready for release. It's still going through a fair bit of development and testing. But this should be ready, I hope, by the end of this year. Those of you who took the course, the workshop, you worked with LC AutoFit, and you worked with the kits that we described, the Mega Kit, which does about 720 compounds. There's a new kit that Alan and Tammy are working on called the Giga Kit that can measure about 1,300 compounds. This uses much less material, about 50 microliters of biological material. The software does its retention time determinations so that you can calibrate things. It picks the peaks, it calibrates things, quantifies. And then the workflow is described within the manual, and typically running it through your mass spec takes about 20 or 25 minutes. It's been tested on a bunch of SciEx instruments. We're just transferring it to the 7500. Hopefully, it'll be done at the end of this month. But it's also being moved to other MS platforms, which include things like Waters and Agilent and Thermo. So there's a suite of kits, the Prime, which measures about 145, Mega 720, Giga about 1,300. These are compliant with ISO standards. They're produced under ISO standards, under ISO 9001, but they allow you to get the data at the level that you need to follow high-level, reproducible standards in reporting and analysis. We're also working on other kits. Christina mentioned the Exposome kit and food biomarkers with about 250 compounds. We're expanding this one to include other exposure and environmental compounds similar to the NHANES set. We're working on a set for drugs of abuse, opioids and others. We have, and I've mentioned already, the mega kit or the NMR magnet kits for wine and beer and milk and juice. But we're also doing wine analysis by mass spec, and this looks like it'll be about 200 compounds. Fruit and vegetable analysis, crop plant analysis, steroids, bile acids, vitamins, medical drugs, pesticides, terpenoids, metals, uremic toxins. So these either exist as kit systems or exist as assays within our lab, which can be transferred into kit format. They're all quantitative. Most are LCMS, but some are GC and others are NMR based. So when we look at the performance of community-based quantitative metabolomics, where we're doing absolute quantification, tools like Magnet can allow 50 to 80 compounds. The GCMS AutoFit about 100 to 110. We've looked at the Prime 145, the Mega 720, and the Giga, which will be coming out early next month, I hope, about 1,300 compounds. Now, because these are community-based, the software access is free, but to put the reagents, which include isotopic reagents and all kinds of plates and other stuff, packing it together, testing and validating, it does cost some money, but it's sold at a cost recovery level. So these things are quite a bit cheaper. So these are systems that can measure anywhere from 80 to 100 different samples. So the costs are relatively less than what you would pay for commercial ones. But I think when you're able to do quantitative metabolomics across platforms, it means you're producing the same readable numbers. So alanine measured by NMR, alanine measured by GCMS, alanine measured by LCMS triple quad, or LCMS Orbitrap, or LCMS QTOF. All of them are the same values. They give you the same quantitative results, and they're all comparable. And that gets back to this point about being able to share data, understand data, and integrate data. So if you're fortunate enough to have an NMR, a triple quad, a GCMS, a QTOF, an Orbitrap, or a QTRAP in your lab, all of these will give you numbers that you can use across the platforms, and you can be confident that they're the same. So just like standardization, quantification matters in metabolomics. I think if, as a community, we adopt quantification, it'll allow metabolomics to move out of the research lab and into the clinic, into industry, into environmental practice, into requirements that the government will ask for monitoring, tracking, or measuring things. So rather than quantitative metabolomics being 7%, I'd like to see it around 90% in the papers that are published in metabolomics. What we need to do, even though tools like Giga are getting up to around 1,300, we need to aim for more. We need to be able to measure about 3,000 metabolites to sort of satisfy the expectation and the required coverage that will make people listen to metabolomics and make it interpretable. That's great for research, but what if we wanted to apply it to the clinic? We need to be able to do this much faster and much cheaper for clinical assays. So currently clinical assays measure about 50 metabolites, but they can do it for as little as $3 per sample. We need to be able to do 300 metabolites, perhaps, for $5 a sample. So quantification will help clear bottlenecks, but so too will automation clear bottlenecks. So when we do metabolomics, and most others do metabolomics, and as you saw in the workshop, it's a lot of work. You're pipetting, you're transferring, you're spinning, you're walking back and forth. It's a pretty manually intensive and fairly tedious process that requires hours and sometimes days of work. If you look at the amount of time, especially for processes like untargeted, sample preparations can take a fair bit of time, depending on how complicated they are, 10 to 30 minutes. Measuring on your instruments per sample, about 30 minutes to run LC or to collect data on an NMR. The real bottleneck is the amount of time it takes to do data processing. It can take up to 2 hours to process or handle or analyze a single sample. And then you can do statistics with, say, Metabolomics, and that's a lot faster. But if you just did this for 100 samples, it would take you about 30 days. That's the average time to complete 100 sample analysis for untargeted. If you do targeted metabolomics without, say, the benefit of kits, but where you're using your local assays, using the available software that's on the vendor system, where you're having to prepare things just in time so you can run it, the total time is more like 20 days for 100 samples. Might be a little more, it might be a little less. But that's if someone wanted to do targeted, whether it's targeted quantitative or just general targeted. The data processing is a little faster, that's where the change is. But what you really need to do is come up with ways of shortening the time for metabolite extraction, sample prep, measurement, and especially the data processing part. So all of these can be sped up, but how do you speed them up? Well, you can simplify them, and we've tried to do that, but you can also automate them. So that's the concept of automated metabolomics. So just as I'd mentioned with some of the commercial tools for doing quantitative metabolomics, a lot of them have also pushed towards automation. So the wine screener, juice screener, food screener, lipoprotein systems that you can buy from Brooker are fully automatic. They have sample changers, they collect the spectra, they process the spectra, and you get a report. It's just sort of press a button and walk home. The lipidizer, when it was being sold, was also supposed to be a black box and press a button and you can go home. Genomics software is not an entire system, but it automatically processes NMR spectra. The Biocrities system, it has things that speed up, so it has a workflow that is much faster, so that instead of 20 days to do 100 samples, you can do it in about 2 or 3 days. And then those of you who are at the workshop, we introduced you to the Mega Kit. That also is similar. It's a workflow that's accelerated. And then the GCMS kits or NMR kits also have an accelerated workflow where a lot of the data processing is accelerated. You can also accelerate the sample preparation, the sample extraction. So Agilent has a nice robotic system called Bravo, and it has an automatic pipetter, it has a shaker, it has a heater, it has vacuum filtration, tip washing, everything you need actually to be able to do or run the kits that we have. There are also clinical chemistry analyzers. These are not mass specs, but they do a lot of clinical chemistry and measuring amino acids. They have barcode readers, auto samplers, they have reagents in little tubes that you can just load up. They have incubators, pumps, stirring units, all in a single system, so that you push a button, walk away, and then 2 or 3 hours you have a report that's on your computer describing the content of everything in the samples. We've been working on our own robotic sample preparation system, and those of you who've ever worked on 3D printers might recognize that this is actually just a 3D printer that we've modified. And this is just showing how slow motion, basically, pulling things out, pipetting, and having different reagents and moving to different positions. It's using a handmade pipetter, but it uses essentially a solenoid valve. It can pump off the tips and replace them. And it is being modified to work about 10 times faster, and potentially can also be set up with a multi-channel pipetter. We're modifying this to also do all of the same steps that you guys in the workshop did manually, but automatically. Again, just using a 3D printer. So with automated data analysis, with LC AutoFit, GC AutoFit Magnet, it's typically about a minute per sample instead of hours per sample. That's a big boost in terms of efficiency. Likewise, making the workflows much more simple, more standardized, also allows you to do this quickly. So with NMR, you just have to spin down, add 2 reagents, load into the auto sampler, and then everything is done for you. So it is truly a walk-away, hands-off automatic system. We can do easily 100 samples a day or better. With GCMS, if you go to 96-well plate systems, it can be sped up a lot. It's not as fast as NMR, and the LC column runs are quite a bit slower, but it can be sped up. Those of you who worked in the mega kit in the lab here also saw how we've tried to keep the process very simple. Yes, there's a lot of pipetting, but you're analyzing 96 samples. So we've kept the derivatization simple. We don't have to incubate things at high temperatures. We have a flow injection system, which is very efficient. The column runs are very short, and a few minutes each. Simple derivatization processes, and then very rapid data processing. And that's all connected to MetaboAnalyst. So with an accelerated workflow where you reduce the time to do metabolite extraction or sample prep or running things through the NMR or the mass spec, and by shortening the data processing time from 60 or 120 minutes per sample to 1 minute per sample, then you can take, instead of 30 days for sample analysis of 100, it's 2 days. That's a lot better. It's 15 times faster. What we're hoping to do is, over the next year or so, is make this even faster. So shrink from 2 days to between 10 and 12 hours. And this would be done in part to make this more acceptable to clinical applications where throughput like this is expected, but also to use flow injection, sort of to get rid of the liquid chromatography phases. So instead of 20 minutes, it's 2 minutes. The sample preps can all be reduced as well. So 10 to 12 hours is our target. Hopefully, maybe this time next year, we'll see. So standardization matters, quantification matters, automation matters. You need to have things that are fast, easy, user-friendly, and I think hopefully from the workshop you guys have participated, you realize that this kind of workflow makes it a lot easier, and hopefully it'll become more popular. I think people can, if they're familiar with playing around with robotic systems, and there's a lot of students who seem to be pretty familiar now. So do-it-yourself automation. Rather than spending $100,000 US to get a robot or $300,000 to get a robot, you could spend maybe $5,000 to get a robot that just uses 3D printers technology. Automated data processing tools. You've used some, I've given you some other examples. Other labs are also making automated data processing tools. So with automation, we really need to be able, at least for the clinic, to get around 300 metabolites measured in less than 5 minutes. That would allow it to move into the clinic. It would mean metabolomics is really in the clinic. For research applications, for those of us, most of us doing research, we'd like to have 3,000 metabolites measured, but to do that at a level of less than 10 minutes per sample. These are possible. They're not going to happen this year. They're not going to happen next year, but maybe by the year after. Not sure what I'm going to be doing here. So the other one is the high cost of analysis with metabolomics. I've mentioned prices and numbers and dollars and the translation to pesos. So I'd mentioned the costs for buying Biocrides kits. I'm not sure if people have recently bought those in Mexico. It varies quite a bit between different countries. Import costs can jack things up quite a bit. But these are costs that we typically pay in Canada. So They are, the small kit about $60 US, $110 US, $150 US for the Quant 500. You can send samples to Biocrides and they will analyze them for you in Austria, but those cost a fair bit. Metabolon is a company in the US. They do analysis. You can measure up to about 1,200 compounds with Metabolon in serum or urine or stool samples. But they're not absolute quantification. It's relative quantification. But you can be certain that the compound identified is correct. So it's targeted non-quantitative metabolomics. So if you send them 2 or 3 samples, it'll be about $300 or $500 or $400. If you send them 10,000 samples, it'll be about $150 US to analyze them. Problem with Metabolon is that the data actually belongs to Metabolon. They get to keep they get to keep all the raw data. You're not allowed to see it. And the measured data also can be used by them for their own purposes. So that's an issue. It's not fair compliant, and this is a problem. If you wanted to use the food screener or the IVD diagnostic systems that Brooker offers, you can't buy the software. You actually have to buy the entire instrument, and the software comes with it. So in that regard, it's really, really expensive. However, there is an NMR service that a company called Nightingale, which is based in Finland, offers, and they do lipoprotein measurement. And again, the number of samples between $50 to $150 US. Again, the data belongs to the company. And depending on what you want to call it, they measure about 25 small molecule metabolites and about 200 lipoprotein ratios and values. So is that metabolomics or is that lipoprotein measurement? It's sort of debatable. So, you can go commercial, and a lot of people do. It's convenient. You can also, if you want to save money, you can try and do it yourself. So those costs are fairly high, but there's also staff costs and efforts of many hundreds of hours. You can also go to core facilities, and some of those are relatively cheap, but then if you're shipping from Mexico or other places, or customs delays, shipping delays, backlogs, wait times, that can also be problematic. You could also go to these low-cost community kit providers and do it by yourself. The advantages are that they're easy to use, easy to run, fast turnaround. The day you get the kit, you can run it. But the staff have to get training. You also have to have the right instruments. If you don't have the instruments, then they don't work for those instruments. So there's a number of core facilities around the world. The Metabolomics Innovation Center is based in Canada. We are one of the nodes, but there are many other nodes across Canada that are all connected. They offer different assays for different prices, but because they are done in Canadian dollars, they're cheaper, usually about 30% cheaper than US ones. We have our subsidized nodes, so the government subsidizes us. We also have fairly substantial discounts for people sending us samples from low to middle income countries. The US has a number of facilities. This was the map of facilities about 3 or 4 years ago, but the UC Davis one, which is in California, is actually very good, and that's one that you can also offer. They don't do quantitative metabolomics, but they do have very extensive coverage. So in the case of TMIC, I've already mentioned how much both the kits but also the assays typically cost. So when the kits are run in TMIC for groups from low to middle income countries, depending on the assay, they can range from $10 to $50 per sample. And it's not just these kits, there are other types of kits and assays that can be run. So if we're talking about sort of an aspirational goal of where we should be, standardization, quantification, automation, cost is important. Cost is a way of democratizing metabolomics. It makes it accessible to everyone, not just wealthy countries or wealthy labs. It's also an issue for clinicians. They're not interested in a 30-day turnaround and paying $500 per sample. They would rather pay $5 a sample and have a 10-minute turnaround. So we need, if we're going to change or get metabolomics used in the clinic, in industry, it has to be cheap, it has to be fast. It's why genomics is used so widely, because the costs have dropped essentially about 100,000-fold over the last 20 years. Cost of sequencing a human genome was $3 billion US. It's now $1,000 US. If the cost of sequencing a genome was still $3 billion, we wouldn't have heard, or we won't be hearing about genomics at all. So the fact they've driven the cost down 100,000-fold is key to its success. We need to do the same for metabolomics. So a goal that we're trying for in terms of research costs, we'd like to see the average cost about $20 US per sample. And for clinical assays, we'd like to see the costs about $5 a sample. And those are what you have to think about if you're also trying to create both assays or methods that could ultimately be used by others. So what I'm going to do, I've been talking for a while. We're going to take about a 5-minute break. People can stretch their legs. If there's still some coffee or juice or something they can get. I'm also going to rest my voice and have something to drink too. So someone could let folks in the back know that we'll start up again. Okay, I think we'll start up here again. We'll finish up in about 25 or 30 minutes here. So another challenge often in metabolomics is that we don't cover very many metabolites. So this has been called the dark matter problem. So when we do untargeted metabolomics, typically people only report 50 to 100 compounds. We identify only 5%. Yet we know there's about 250,000 metabolites in the human metabolome. So relative to proteomics and genomics, our coverage is very, very low. And because the coverage is low, a lot of clinicians, physicians have doubts about the utility of metabolomics because it seems we're only measuring a tiny fraction. In this case, there's lots of compounds that we know about, but when we consume things, or when things are in the soil, or when the microbes get them, they are transformed. And that transformation process actually changes them a lot. Changes from things that we know to things that we don't know. So right now, the best estimate we have of how many compounds are in that dark matter, it's not 200,000, it's not 500,000. It's looking like it could be up to 15 million compounds. So we could potentially address this as if we could, get $15 billion US dollars from someone. We could isolate all of these things. We could synthesize them. We could run them through artificial guts or liver microsomes and process their metabolites and collect all the things that are in the high production volume chemicals, of which there's almost 1 million. All the known drugs and pollutants that we can get our hands on. But this would cost, as I said, about $15 billion. Or we can use computers to do this. And the cost is a lot less, more in the order of 1 million US dollars. The concept is called in silico metabolomics, and it's something that my lab has been working on for about 10 years now. The idea is to take the data that we know about the known compounds. These are databases I've talked about, or some of you might know, from the Human Metabolome Database, the Natural Product Database, Food Database. but then to use software called biotransformer, generative models that use machine learning, and then to use other tools to predict the spectra, the retention times, the retention indices, the collision cross-section, the infrared spectra, for all of these. So instead of having just a database of a few thousand, which is what we currently have, this would be a database of 15 million compounds with 15 million NMR spectra, 15 million MSMS spectra. And then this would be a reference that you could take what you measured and see if it matches anything in that database. So the tool we developed to do metabolism prediction is called Biotransformer. It takes a compound, runs it through the phase 1, phase 2, gut microbial, abiotic, promiscuous enzyme, multi-step transformations. We've gone through several versions. The most recent one is much, much better. And we're running it right now on all the compounds in our libraries. It's been running and will be running for several months. And we expect it'll generate about 10 million compounds when it's finished. This will be then put out there for people to use along with their predicted spectra. Another approach we've been using is called generative modeling. It's different than using, thinking or imagining how enzymes work. This one's just taking chemical structures and converting them to text. And so it's a chemical language model. Just like a large language model uses advanced machine learning, it takes those known structures, learns their features, what they should be like chemically, and starts saying, I got an idea, so I'll generate some more ones. And give it a few thousand training examples. It can generate millions or even billions of structures. Many of them are replicates of each other, so if you make sure you've consolidated them all down. In this one example, we produced from 1 billion structures, we whittled it down to about 9 million structures. These were things which were called novel psychoactive substances, or the street drugs, opioids. What we found was that this method allowed us to create a huge database of compounds that have never been synthesized, or at least we didn't think they had been synthesized. But we did a test where we talked with police services and forensic chemist services in the European Union, and they had kept about 120 compounds from us when we did our training, and they said, are any of these 120 compounds that they knew about, were any of them in our database? And so 93% of them actually were, and the 7% that weren't were actually not novel psychoactive substances. So effectively, it was 100% correct. So it had predicted all the compounds that eventually showed up on the street, and it's still predicting compounds that are showing up on the street that have appeared since then. We've applied the same idea not to psychoactive substances or opioids, but to human metabolites, and this database is called DeepMet. We now know that the frequency at which this language model generates structures is a reflection of how likely that structure is to exist in nature. So we have counts, and these give us what are called a priori probabilities. And so we can use those numbers, those probabilities, to help identify novel compounds. Ones with high probabilities probably are in your system. Ones with incredibly low probabilities, probably not there. When we combine that with the ability to predict mass spectra or tandem mass spectra, we can do really well. We've compared it to other programs for novel compound prediction like Sirius, and it turns out to be about 50% better. More recent improvements are probably about 75% better. These are examples of some of the novel compounds we've identified, real compounds, which were not in any library, not in any database, but which were in these generative databases within these in silico predicted spectra. So a lot of our work has been focused on saying, okay, we've got these structures, whether they're from biotransformer or whether they're from the chemical language models, but they're structures. when you run through a mass spec, you don't get a structure, you get a mass spectrum. When you put a structure into an NMR, you get a spectrum. When you run it through a liquid chromatography, you get a retention time. Those are the observables. So when it comes to spectral prediction, it's something that people have been trying since the 1960s. The very first AI program was a mass spectrum prediction program called Dendril. So it's been of interest to computer scientists for more than 60 years. Advances in machine learning have actually moved from where we were in Dendril 60 years ago to the point where we're getting pretty good spectral prediction. These are examples. We've been working on versions 1, version 2, version 3, version 4. Version 4 is the one that's been published, and we're just sort of showing, comparing red versus blue. Those are predicted versus observed at different collision energies. And you can see how closely they match, at least version 4. Version 3, not so good. And this is illustrating how we've improved over the years, from 2016 to 2018 to 2021. 100% is perfect. So the latest version is still not really passing in terms of performance, but that's not needed. It doesn't have to predict the spectra. So then when we look to see, or it doesn't have to predict them accurately, if we compare what we get with the standardized test, we can still get about 80% of the compounds identified correctly using these predicted spectra, even though they're not 100% matches. More recently, we used more advanced machine learning methods. So you can see this is in 2021, so it's now 2024. We're using a more sophisticated graphical neural net. That's what a GNN is. The program is called FragNet. And this is the performance. So instead of at 40%, we're at 80%. At 10 electron volt collision energy, 68%, 59%. And now we're getting around 95%. And again, the performance, even with CFMID4 for a more complicated structure, kind of failed. With FragNet, it passes very easily. So we can predict mass spectra now quite accurately. What about retention times? What about retention indices, ESIMS? This is a tool for predicting retention time. It's being submitted for publication. The website is up. But it allows you to predict retention times quite accurately within about a minute or two of where they come off, if you've got, say, a 30-minute run. It works for many different chromatographic methods. It also allows you to just train on your own method, and then it'll predict the retention times for every compound in the HMDB. So you'll have retention times, hundreds of thousands, which then allow you to zero in on your molecule. You can do this with also retention indices with gas chromatography. And retention indices are much easier to predict and much more accurately predicted. So retention times, you have errors that are probably not the best. Here we're talking about errors of a few seconds. And we have run this on many millions of compounds and their derivatives. There are also new methods for predicting GCMS or EIMS spectra that are very accurate. Again, blue is measured, red is predicted. They're not perfect, but they're pretty close. So typically the performance is around 65%, so 100% is perfect. We've also added tools to predict the ions and label and annotate the spectra. So in the case of GCMS, we've combined these. We combined the retention index prediction and the MS prediction into a web server that just came out called GCMS ID. And so it's been run through hundreds of thousands of compounds in HMDB and NIST and the Norman suspect list. And so now you can upload your retention indices and your observed mass spectra, and odds are you'll get a match. We're doing the same, or hope to do the same, for LCMS, where we combine FragNet with retention time prediction, and this too would hopefully give you much more accurate predictions. So for coverage, we'd like to be able to increase the number of compounds, shouldn't be ERs, but years, 500,000 from 250,000. I am hoping that in silico metabolomics will actually become pretty routine, especially for untargeted metabolomics. and that it'll allow people to not just identify 100 compounds with untargeted, but routinely about 10,000 compounds with untargeted. And then it'll also allow us to expand that list of meaningful targeted metabolomics that appear in the next version of the GigaDate kit to about 3,000. And if we can do that, then I think we'll pass that barrier where clinicians really believe us. I'll very quickly talk about the challenges with large equipment. Most of you are familiar with how expensive things are if you use NMR, how expensive mass spectrometers are, how much they weigh, their very large footprints. So this is a challenge. It prevents many labs from pursuing metabolomics. It's certainly an issue in low to middle income countries. They're complicated pieces of equipment and they scare people away, so that limits the number of users. So if we can make things small, simple, and cheap, that would be better. So can we miniaturize metabolomics? So people are. They're making benchtop NMRs, and these are actually remarkably good. They give very good spectra. They're being used for metabolomics. They can perform multi-channel stuff. They're being used in the clinic now. You can do 2D NMR. They have very good line widths, and they're only about $80,000 US. There are also portable miniature GCMS systems, and the costs for these are in the order of $12,000 to $15,000, and they function just like a regular GCMS. There are other things called electronic noses that measure volatile compounds. And these are about $10,000. They don't use a mass spec, but they use different electrodes to detect volatile compounds. It's kind of like your nose does, but it's using electrical inputs. And then you don't get a compound identified formally, but you get patterns and profiles. And they can be modified or trained so you can deconvolute the data to actually identify compounds. People have been able to identify bacteria using an e-nose. There are other applications. We've been interested in adapting colorimetry to low-cost metabolomics. So a lot of things like the GCMS and benchtop NMR or e-nose are $10,000 to $80,000, but could we make something that's $1,000 or $100? Colorimetry is the cheapest way of measuring things. I think everyone's done it at least once in their life. And we've been working on enzymatic-based assays, so to do metabolite measurement by color, to measure carnitine in this case, or ascorbic acid, or creatinine, and to do it quantitatively. So it's not just saying it's there. It has good fits to the observed measures that we do by LCMS and the ones that we get from the color charts. And we've done it for about 20 different metabolites. Some of these are highly relevant for medical testing, glucose, creatinine, creatine, lysine, urea. And we've also made a portable colorimetric device. We've published on it this year, it just came out. But we've been modifying the device and to make it fully automatic. The idea is press a button, walk away, and it measures these metabolites quantitatively. It's not like a urine strip where you dip it in and colors are there, but it doesn't tell you the concentrations. This tells you the concentrations. And the whole system is built using a low-cost 3D printer. These are the guts of the system. It has pumps, it has color sensors, it has a pipette system, a syringe filter. It uses little cuvettes, and the output can be sent out through Bluetooth to your iPad for results. So this works. We're adapting it to work for more. And it's actually being used for colorimetric testing for colorectal cancer with a project that we're doing in Nigeria. So if we can make things more portable, we could democratize metabolomics. Portable instruments could be in the doctor's office. It would make home monitoring, physician monitoring, disease prevention much more accessible. We need things to drop from $1 million US to $5,000 for an automatic metabolomic system that could measure maybe 30 metabolites in about 5 minutes. We could also try and make things for at-home monitoring so that you could track things if you happen to have a condition. I mean, we've got glucose monitors that measure glucose inexpensively. Can we do that for multiple metabolites, not just glucose? Because that's really all there is right now. And we've been working on methods in the systems that could and should be able to do that for, in some cases, just less than $1. The last one I'll talk about here is just how do we get past the translation of findings to the clinic. So since 1970, so 55 years, there's been 1.2 million biomarker papers published, but only 250 have made it into the clinic. In terms of proteomics, using mass spec, none of them have made it into the clinic. In terms of microarrays and transcriptomics, only 5. And in terms of genomics, there's only 130 approved gene tests. Now, a gene test can measure 100 mutations, so they can say that genomics has tens of thousands of tests, but boil it down, it's still 130 gene tests. So all the money we've invested in omics, we haven't really produced a lot in terms of impact for medical biomarkers. How does Metabolomics do? Well, companies like Metabolon have done things. Quest Diagnostics have done things. A company in Canada called MTI. NeuroPoint and Stemina have developed some metabolomics-based biomarkers. So we can maybe say there's 6 sets of markers that have come out. So we're better than proteomics. We're better than transcriptomics. Not as successful as genomics. None of them has been a real blockbuster. Metabolon pulled their stuff. But the perspective from many funding agencies is that because we didn't get hundreds and because we didn't make the headlines and we didn't have presidents and prime ministers talking about these biomarkers, that metabolomics has failed to deliver. And that's worrisome. So how do we change that? So I think what we can do is perhaps change the message. Maybe we should start focusing on things that are a little easier. And maybe we should start teaching metabolomics researchers how to move these things into the clinic so they aren't just simply publishing them, but they're actually translating them. Maybe we should also think about, instead of just the clinical market, think about the wellness market. Think about the nutrition market, which is generally easier to get into. Now, there are successes. So you can point to the 6 assays from the metabolomics companies, but when you think about the number of approved assays that measure chemicals for the clinic, so that includes metabolomics and clinical chemistry, there's about 330. So the message is actually metabolomics is winning. It's beating out genomics, it's beating out proteomics, it's beating out transcriptomics. If we count the clinical chemistry assays, and clinical chemists are loath to say that they do metabolomics, but when they're measuring 50 compounds at a time, I call that metabolomics. The biggest success, as we highlighted in the workshop, is that newborn screening. That's using metabolomics. It's done 450,000 times a year in the US and probably 700,000 times in Europe and about 200,000 times in Mexico. Every year, every person under the age of 30 living in Mexico, Canada, the US, and Europe has had a metabolomic test. What's more is that the metabolomic test, if you're positive, we come up with precision therapies that prevent you from suffering from the disease. So if you have biotinidase deficiency or phenylketonuria, you can live a long, normal, healthy life by using these precision diets, these special clinical foods. It makes a huge difference. So the fact that we can do precise, quantitative, personalized diagnoses for more than 50 metabolic disorders through IEMs, the fact that we can deliver precise diets, we can deliver advice for lifestyle changes, we can give them medical foods that save their lives and improve their lives. So newborn screening has been applied to about 300 million children, and it's probably saved the lives or improved the lives of about 1 million, because about 1 in 300 people, our infants, have an inborn error of metabolism. So if we include IEM testing, but also clinical testing for things like glucose, creatinine, cholesterol, other things that are routine chemical tests, they've been performed on about 7 billion people at least, and have probably saved or improved the lives of about 1 billion people. And that's more than all the genomic, all the proteomic, all the transcriptomic, all the microbiome tests have done or ever will do. So metabolomics is making a difference. Call it clinical chemistry, call it metabolomics, call it newborn screening. It is changing lives. But we don't have the voice to tell people that. We need to tell our politicians, our funders, other scientists, that we are succeeding. We didn't fail to deliver. We have delivered. Can we keep this going? So I think we need to teach you. We need to teach other people how to do clinical metabolomics, how to do quantitative metabolomics, to show them how they can translate their discoveries into the clinic and how to make them useful for the clinic, and to report that information to their funders. The pathway is challenging to take a discovered biomarker, to validate, refine it, to release it, to do the lobbying, to get the approval. We teach you about this in some of the courses we offer, but because it's such a long and winding road, we often have a lot of failures. There's only about 0.01% of the biomarkers that people discover ultimately make it into the clinic. So the clinic market is hard and challenging. It's called the white market. It's where you have to get ISO approvals. But there's another market called the gray market, where it's direct to consumer, where it's wellness testing or exposome or diet testing, curiosity testing. This is what 23andMe and Ancestry.com do. And they're making a lot of money, and this is also feasible. So what's happening? Well, rather than waiting 10 years for FDA approval, people are moving out to create their own companies that focus on precision nutrition, precision medicine, precision wellness. These are examples of some of the companies that are doing pretty well. They use metabolomics, they use exposomics, they use microbiome analysis, they use machine learning, and they use databases. The concept basically is it's not children or infants, it's adults. Take a blood sample, take a urine sample, have that analyzed with machine learning, use the databases that we've made available publicly. Most of them use our databases, and then come up with a plan for exercise, nutrition, diet supplements, medications that are personalized or precise for the individuals that are going through the testing. This is an example that comes out from one of these wellness companies of this particular person where their amino acids and acylcarnitines are measured and quantified and compared to reference values. Red means bad, green means good, yellow is borderline. By comparing to reference sets, you get this. This is why quantitation is so important, and how you can get a really detailed, simple to understand medical report. This is an example we learned the other day about healthy obese and unhealthy obese. So this is a person who is unhealthy with high acylcarnitines, high branched chain amino acids, high glucose. This person has both diabetes, untreated, well, not well treated. The acylcarnitines tell us that, the high levels. The branched chain amino acids tell us that. They also have chronic kidney disease. Here's another person with a similar BMI. Everything's green. So you can get these, you can measure this. So they look the same, but metabolically one is totally different than the other. And they're about the same age. For those of you at the workshop, we talked about how you could do regular metabolome monitoring, regular testing every couple months. This is an example with one company called Molecular U, where they took 120 people, measured their metabolomes, assessed their dietary health, cognitive health, kidney health, liver health, and ranked them. And most everyone was sort of at a failing grade. They gave them a custom diet, nutrition, supplement, exercise, lifestyle advice, and then 3 months later, everyone improved quite significantly. All of them were passing in terms of their health. All of them were green, basically, in terms of the markers. The other example I've given is a woman who had been monitoring for the last 4 or 5 years using metabolomics and proteomics. She was normal in 2018. She was mostly normal in 2019. She seemed normal in 2021, although there's some cautions given to her. 2022, everything went red. And so she was told to go to her doctor and have a CT image because it looked like she either had ovarian cancer or pancreatic cancer based on the readout from the metabolites and the protein data. They saw a tumor. It grew within 2 months. They resected it. And it was just about to explode in their terms. But because they removed it, she's been cured. Readings in 2023 are basically normal, 2024 are even more normal. So she was cured from pancreatic cancer, yet pancreatic cancer has a 95% mortality rate. This is one of the first times that anyone had seen stage 1 pancreatic cancer. You could only catch it through longitudinal metabolomic monitoring. So what I'd like to see is actually metabolomics moving to the clinic, but I'd also like people to tell us, tell the world about the successes that metabolomics has, about how quantitation could allow metabolomics to become a standard clinical tool. I'd like to see more metabolite markers making it into the clinic, improving that by maybe a factor of 10. I'd like to have more people doing clinical metabolomics, but knowing how to make biomarkers translate to the clinic. And that eventually metabolomics would be the tool of choice for precision medicine and precision nutrition. So my talk is focusing on how we can move things forward and how we can use standardization, quantification, automation, lower costs, better coverage, more portable platforms. If we do that, we will be able to move to the clinic. A lot of my career, a lot of my work in the lab is focused on those things. And that's been, I think, my view is it's how we can translate it. I don't want to be the only person trying this. I'd like to try and teach others and show others and encourage others to do that. And so the long-term success for those of you wanting to do metabolomics depends on how much you'll be able to adapt to these concepts and evolve them, join them, move them forward, develop your own, but as long as it moves us towards better standardization, better quantification, more automation, we can make metabolomics matter. So with that, I really want to thank everyone for listening, but I especially want to thank Yamile and Carla for all their work, for Alan and Tammy teaching you guys in this workshop that you've attended, Francisco for hosting us, and for all the staff at UNAM, Zacatecas, Cinva staff who've volunteered and helped. There's been other people at TMIC that have helped put the work that I've described here together, the kits as well, and then all of you who've attended the workshop and today. So thank you very much.
I think after this excellent, impressive conference, I'm sure that we will make metabolomics matter, and we will work for sure together to overcome all the challenges and following the opinion of one expert, a person who have been dedicated all his life to metabolomics and in favor of the community, society, and science in general. So it's really, really impressive and totally happy and excited of having this opportunity. If you have some questions, Dr. Wisher, we can just have a little time for that.
So, Professor, I have a question. Sometimes the softwares or the databases have different fragmentations patterns. What happened in this case? Is the equipment or it's the conditions? What is in this case?
Yeah, I think different spectra will show up from time to time, and that if you compare them one day to the next day, they might have an overlap of about 90%. And that's particularly, it's a condition of the instrument, the fragmentation conditions. They're not exactly reproducible. There's elements of tuning. So unlike NMR, where you can measure the same spectrum over and over and over again, it'll look the same, mass spec has that variation just because it's measuring things that explode. So explosions happen differently each time. But 90%, 95% similarity, that's close enough.
which sector do you think is like the fastest developing in that area? I mean, environmental or medical or food sector?
Yeah. So in terms of fastest evolving, medicine is always the slowest, always. I mean, they're still using paper records. They don't use electronic records. So the fastest evolving will probably be environment. You'll see the next one probably in food, and then the slowest will be medical. And it's just the whole hierarchy of approvals that are required. So environmental monitoring doesn't need as many approvals or government assessments. In terms of how close are we to having a comb that tells us whether we have cancer, we're a long ways away from that. I think the concept of urine testing, at-home urine testing, is something that could happen maybe in the next couple of years. And you can't detect every disease, but you could probably detect anything from diabetes to kidney cancer to a few other things. There are, I think, ideas of electronic noses, GCMS systems that might be cheap that could detect whether you have Parkinson's disease or are developing Parkinson's disease or TB. So the volatile sensing area is probably going to be the most rapidly developing one for medical testing. But those are still going to be a few years away. Okay.
Firstly, thank you for this amazing presentation. And I'm curious about on the aspirational goals section that you mentioned for the low-cost DIY the use of 3D printer. Can you tell me more about that?
Yeah, so a 3D printer is basically a robot. It has things that can move left and right and up and down. And a lot of robotic systems, to be able to move in 3 dimensions, are all you need. You have to know something about electronics, and you'll have to sort of replace the board that's used in that. So if you happen to have people with good knowledge of Arduino or Pi Raspberry or electrical engineering, they can modify 3D printing systems to do that sort of thing. You can talk to some of them down here who have done that. There are people in our lab who are doing it. We're aware of others who are doing it. And so it's a really cheap way because you can buy a 3D printer for not much. You can modify it with Arduino and Pi Raspberry with not much. It takes time. It's not easy. But this is a way forward, and the net cost for the materials is probably less than about $5,000 in total. So it's quite a bit cheaper than $100,000 or $200,000 for other types of robotic systems, which largely do the same thing. Okay.
How many times was the development kits with all of the communication about the calibration optimization? All the time?
The time to develop the kits? So it's getting shorter, largely because of the processes that we've learned, because the first kit probably took about a year and a half. Now I think we can probably create kits in about 1 or 2 months. Scaling to go to a very large kit takes quite a bit more time, but if we're wanting to have like a steroid kit or a plant metabolite kit or another one, that's taking from the big kit and making it smaller or just adding a few more compounds. Alan and Tammy can probably give you an exact estimate because they've made a lot of them. But it's getting faster, partly because we've learned a lot. We have the software that helps do this much more easily. if someone were not in our lab but wanted to do the same thing, it would take, about 2 years to make their very first kit, and then about 6 months for the next one, and then 3 months for the next one. So it speeds up as you do it. And you can also take existing kits and then modify them, just like we modify 3D printers. We don't make our 3D printers, we modify them. So that's also another way of getting a kit more quickly put together.
Right now, we will have a close of a workshop making Thank you so much.
Good afternoon, everybody. Good afternoon, the attendance of this course. Buenas tardes a todos. I'm pretty sure all of you are exhausted, but you don't even notice that because you are so excited that you learned a lot of things in 9 to 6 all week long, from 9 to 6 all week long. So it has been exciting for all of you. That's very interesting for us. And to make this course come true, many people has intervened. We have the support from many people, so I have to introduce some of you. On behalf of our School of Chemistry director, I have to introduce you Professor Itzel Guerrero Rios, who is the research secretary of this school. Itzel. And of course, you all know Professor David Wishart and all of his team, who has been mostly teaching you all of this new stuff for some of you. Even something is not so new for you. Everything has been really, really impressive. Professor. And on behalf of the Metabolomics Association of North America, the General Course Coordinator, you also have been working with her all week long, Doctora PhD Yamile Lopez. Is Octavio here? Arregin? Yes. Well, we succeeded because we had to switch instrument and we needed another one, and SciEx provided a new one and installed it in 1 day. And the next day, we were already taking data, collecting data, and so on behalf of SciEx, the West LATAM manager, Octavio Arregin. And Professor José Luz González Chávez, who is the head of our analytical chemistry department. Most of the places you were working on belongs to this department. So I have to leave space to Yamile, who has to speak a little bit before declaring this closed.
Okay, I don't have a signal here. Okay. Okay, something is getting wrong. Well, it has been an intense week. I think most of us were exhausted. Sometimes, maybe on Tuesday, Wednesday, where the practical sessions were taking place. For sure, I need to acknowledge Tammy and Alan. They were really, really, really important and critical for me to do that possible. innovations, which we had conference. I would like to acknowledge Dr. Carlos Aguilar. He's not with us, but he was present here with the conference, and also Natalia Vasquez from National Institute of Medical Science. All our founders, for example, Uno Biolac, which was the main founder, but also the Metabolomic Innovation Center, who keenly provide the kits for making possible the practice. Also, Instituto de Investigaciones Biomédicas, Universidad Autónoma de Zacatecas, some providers, for example, Viresa, and of course, most importantly, SciEx and Faculty of Chemistry, School of Chemistry. Finally, we had 43 attendees from Colombia, Brazil, Argentina, Costa Rica, and of course, Mexico. We had some great opinions, some comments in social media. For example, Uno Biolac recognized our work, the workshop, and telling us that breaking walls through knowledge is the best way, mainly when we are doing that, helping and learning from each others. We had 3 or 4 theory sessions. We had 3 sessions of practice, hands-on sessions, 2 days in the lab, 1 day for data analysis using L3 out of it, and also meta-analysis. We also had 3 short presentations, 1 conference from, as I said, Carlos Aguilar Salinas. And at the end, we learned basic principles of target metabolomics, how to do comprehensive analysis in biological fluids, how to use ready-to-use kits for metabolomics. We use Timic Mega assay this time. How to work with fully automatic software for data processing, for example, LC out of it, and also meta-analysis for making statistical analysis more faster, more easier, and more intuitive. We had new perspective presenters here showed as well Carlos Aguilar Salinas and Dr. Cristina Andrés La Cueva, how to use and how to explore multiple fields applying metabolomics. Now we have more tools available to decrease time-consuming steps as excellently explained by Dr. David Wisher, and also to reduce cost, which is one of the limiting things here in America, North America also, but mainly in Latin America and South America. For example, these steps involving sample preparation, analytical method development, that it was the last question from Maribel, data processing, data analysis. We knew also about one program, the Research Hotel program at Metabolomics Innovation Center, which is available for students, for you, for postdoc, and you are also welcome to apply. You had a chance to establish new connections, new networks, new collaborations, joining efforts to make metabolomics matter. And behind all that happened, we want to recognize the effort of all the instructors, the volunteers, friends, colleagues, and also all of you to make it possible. Of course, 2 key persons, Francisco Rojo and also Elba, thanks a lot. You you were working a lot for making it possible since maybe 3 months ago. And also your team, I have no pictures, but he's Iran, Jerónimo, who were involved in all the stage of the workshop preparation. Of course, SAIEX, Mexico, Eduardo Vélez, my friend Edgar Vázquez. Thanks, Octavio Orellín, for being involved since the beginning of the idea and since we applied to ONO Biolac for getting the funds. Isabel Ibarra, Silvia Ivonne Mora, Maria Carla Ferrer, thanks a lot for the hard work you did. Of course, my students, Diego Alvarado and David Garcia Lopez, you will have more challenges from this day and in the future, of course. Your instructors, Tammy and Allen, this is how Tammy and the second day of the practice, so it was really intense for sure, and as far as she mentioned, it has been the more intense workshop he has been involved in. And the winner of the week was for sure Nancy Shirley Garcia. As Dr. David Wisher said, may I help you? And thank you, Nancy, because Nancy told me a week before the workshop, I had a lesion on my feet, and I said, okay, no problem, but I never imagined that it was a serious lesion, and Nancy is here with us. With Nancy, we acquired another key and important person, Hector. Thanks, Hector, a lot for being here. And today we are saying hasta pronto, and see you in Colombia 2025. We will be working for make it possible in Colombia 2025. We're talking about some exciting topics, for example, exposome, nutrition, environmental challenges, and we will let you know once the applications could be ready to apply, and of course, all of you are invited. Thanks a lot, and we will have a short time during the lunch to share and to talk more about and to feel happy because it was possible this week. So, following question from Carla, Silvia, and Isabel, because we will have a lunch for the attendance in the course. In the class for las casas, Club del Académico, it's supposed to be here at 1:30 because we knew only 2 days ago that it was not possible to get there at 2 p.m. because for logistic questions are there. So follow Maria Carla, follow Cynthia, and we expect to join together in faculty group or Casa de la Academia.
Okay. So finally, I have to declare this course closed. Thank you, everybody.